Some nights, you find yourself looking up. Maybe it happens without thinking, a walk to the car, a moment on the porch, a window left slightly open to the cooling air. And there they are, quiet, impossibly distant, scattered across the dark, like something someone forgot to put away. You might not stop long. Most people don't. But something in you noticed. Something always notices. If you'd like to stay here for a little while tonight, just here, just still, just listening, you're welcome to. There's nowhere else to be. And what we're going to move through together is slow and gentle and true. So only if it feels right. Let yourself settle in. Now, let's drift. There's something scientists have quietly observed about the human relationship with the night sky. When people look up at stars, really look, not glance, something in the body begins to slow. The breath lengthens. The muscles that have been holding the shape of the day start to release. Researchers who study the psychology of awe have noted that this response is almost involuntary, as if the brain recognizes on some level that what it is seeing is simply too large to be processed with urgency. And so it stops trying. It simply opens. What you're seeing when you look at the night sky isn't decoration. It isn't background. It's a catalog, an enormous, ancient, ongoing catalog of different kinds of fires. And no two of them are quite the same. For most of human history, we had no way to know that. Stars were stars. Points of light that appeared at dusk and vanished at dawn. Some were brighter, some steadier, some seemed to wander, but the idea that they were fundamentally different objects, different in size, in temperature, in age, in the very fuel they were burning, that understanding came slowly and mostly within the last few hundred years. It's a quiet kind of strangeness when you hold it for a moment, that for thousands of years, poets and sailors and farmers looked up at those same lights and never knew they were looking at a family of completely different things. The way you might spend years in a house before realizing that each room holds an entirely different kind of silence. The science of classifying stars began in a meaningful way in the late 1800s and early 1900s. It didn't begin with telescopes pointed at the sky exactly. It began with something more delicate than that. It began with light. When light from a star passes through a prism or through a specialized instrument called a spectroscope, it doesn't stay white. It separates. It spreads into a long band of color, the full range from deep red at one end to violet at the other. And running through that band are thin, dark lines, little absences, little gaps where specific wavelengths of light have been absorbed by the gases in the star's outer atmosphere. These lines are like a fingerprint. Each element, hydrogen, helium, calcium, iron, absorbs light at its own precise set of wavelengths. So by studying which lines appear and where astronomers can identify what a star is made of, how hot it is, and even how fast it is moving toward or away from the Earth. It's a beautiful method when you think about it. Reading a star, not by looking at it directly, but by listening to what its light is missing. In the early decades of this kind of stellar spectroscopy, thousands and thousands of stars were classified by a team of astronomers working at the Harvard College Observatory. Many of the people doing this detailed, painstaking work were women known informally as the Harvard computers, who spent years measuring and cataloging the spectra of stars by hand. One of them, a woman named Annie Jump Cannon, developed a classification system that is still used today. She processed hundreds of thousands of stars during her career, often working at remarkable speed, earning a reputation as one of the most productive astronomical catalogers in history. What emerged from that work, from all those hours, all those spectral lines, all that careful attention, was a pattern. Stars fell into groups. Not randomly, not arbitrarily, but in ways that reflected something true, about their nature, their temperature, their color, the stage of life they occupied. Researchers have since come to understand that a star's color and temperature are deeply connected, almost inseparably so. The hottest stars glow blue-white. Slightly cooler stars shade toward white, then toward the pale yellow of our own sun, then orange, and finally red at the cooler end. It's the same principle that makes a metal rod glow red when first heated and shift toward white or blue as the temperature rises. The physics of radiation doesn't change just because the object doing the radiating is 1,000,000 times larger than anything on Earth. And so in a sense, every star you can see is showing you its temperature in the most direct way possible. It is wearing its heat as its color. There's something quietly grounding about that. The idea that what looks like mystery, all those lights, all that variation, can be held gently inside a pattern. Not in a way that makes it smaller, but in a way that makes it legible. The way certain kinds of understanding don't diminish beauty so much as deepen it. Some scientists have noted that this is one of the things people find most calming about astronomy as a subject. It is vast beyond any intuitive grasp, yes, but it is also governed by laws that remain consistent. The same physics that shapes the light from a star 400 light-years away is the same physics that shapes the light from a candle in a quiet room. There is something about that consistency that the mind finds restful. Something that feels on a level below language, like a kind of reassurance. The universe is not chaos. It is pattern. Patient, deep, persistent pattern. The classification system that Annie Jump Cannon helped develop arranges stars into a sequence based on their temperature. The groups are labeled for reasons that are partly historical and partly the kind of thing that survives, mostly because it's too established to change, with the letters O, B, A, F, G, K, and M. Astronomers sometimes use a gentle mnemonic to remember the order "Oh, be a fine girl, kiss me," or the gender-neutral version "Oh, be a fine guide, keep moving." Each letter represents a temperature range, a set of spectral characteristics, a color, a personality in a way. The O and B stars at the top of the sequence are the hottest and the bluest, enormous, brilliant, burning at temperatures so extreme they radiate mostly in the ultraviolet range, which human eyes can't even detect. The stars that glow blue in the night sky are offering you only a fraction of what they're actually producing. Moving down the sequence, temperatures soften. The A stars are still quite hot, white or blue-white, recognizable to any careful nighttime observer. The F and G stars shade into the familiar pale yellow of sun-like stars. The K stars move toward orange, and the M stars, the coolest in this original sequence, glow in deep shades of red and orange, so cool, relatively speaking, that their surfaces can host certain molecules that would be torn apart by the heat of hotter stars. This sequence, as it turned out, also had a relationship to something far more consequential than temperature alone. It had a relationship to mass, and mass in the life of a star is everything. Researchers who study stellar evolution, the long, slow lives of stars from birth to death, have found that a star's mass at the moment of its formation determines almost everything that follows. How hot it burns, how bright it shines, how long it lives, and how it ends. A star is at its core a negotiation, a continuous, unceasing balance between two enormous forces. On one side, gravity pulling inward, trying to collapse the star into itself. On the other side, the pressure generated by nuclear fusion, the process by which hydrogen atoms are fused together in the star's core to form helium, releasing enormous amounts of energy in the process. For as long as a star has hydrogen to fuse, the outward pressure of that energy pushes back against the inward pull of gravity. The star holds its shape, it shines, it continues. But that process has a clock, and the size of the star determines how fast that clock runs. It seems counterintuitive at first. You might expect a larger star one with more hydrogen to burn to live longer. But the relationship works the other way. The more massive a star is, the stronger the gravitational pressure pulling inward, and so the more furiously the nuclear fusion at its core must run to push back. Massive stars consume their fuel not slowly, but at an almost reckless rate. A star 10 or 20 times the mass of our Sun may exhaust its hydrogen fuel in only a few million years, which by the scale of cosmic time is almost no time at all. The smallest stars, by contrast, the dim, cool red ones, burn so slowly and so efficiently that they may live for hundreds of billions of years. Some may still be burning long after every other star in the universe has gone quiet. There's something softly remarkable about that. The smallest fires lasting longest. Tonight, all of this is happening above you. Or rather, all of this has been happening, and the light from it is arriving now, carrying news of fires that have been burning for millions of years. The star you're seeing is not the star as it is. It is the star as it was. The light traveling to your eye left its source long before you were born, long before your city existed, in some cases, long before our species began to walk upright. The night sky is not a present tense thing. It is a layered archive, a collection of different moments arriving together, looking like stillness. Scientists sometimes describe this as looking back in time, though that framing can make it sound more dramatic than it actually feels in the quiet of a dark night when you're simply lying still and looking up. It doesn't feel like time travel. It feels more like receiving, like something distant, reaching toward you with great patience, like a letter that took a very long time to arrive. And in the light of each of those stars, all of the variation is written. The temperature, the color, the age, the mass, the stage of life. All of it encoded in the spectrum, waiting quietly for the kind of attention that tonight you just might have enough stillness to give. There are so many kinds of stars, and we've only just arrived at the beginning of understanding them. In a little while, we'll move into the first of those kinds in depth, the smallest, the most common, the ones whose patient fires may outlast everything else in the universe. But for now, there's no need to go anywhere. Just the dark, just the quiet, just the light that has been traveling toward you for longer than you can quite imagine, arriving softly all at once. The smallest stars are also the hardest to see. On a clear night, with no moon and no city light bleeding into the sky, you might count a few thousand stars with the naked eye. But of all the stars in our galaxy, the hundreds of billions of stars that fill the Milky Way, the vast majority of them are invisible to you. Not because they're hidden behind something, not because they're too far away exactly, but because they simply don't produce enough light to reach you across the distance between you and them. They are there. They are burning. They have been burning for longer than our sun has existed, but they burn so quietly, so modestly, so far beneath the threshold of what human eyes were built to detect that the night sky you grew up looking at gives almost no hint that they exist at all. Astronomers call them red dwarfs, and they are by a significant margin the most common type of star in the known universe. If you were to take all the stars in our galaxy and sort them by type, roughly 7 out of every 10 would be red dwarfs. Some estimates place the fraction even higher, closer to 3 out of every 4. They outnumber everything else so completely that every other category of star, the brilliant blue giants, the sun-like yellow dwarfs, the enormous supergiants, all of them together make up a relatively small portion of what's actually out there. And yet, for most of human history, we didn't know they existed. The reason is straightforward and a little humbling. Red dwarfs are simply too dim. Even the nearest red dwarf to our solar system, a star called Proxima Centauri, which is also, as it happens, the nearest star to the sun of any kind, is completely invisible without a telescope. It sits just over 4 light-years away. In cosmic terms, it is practically next door, and still, you cannot see it. There's something almost meditative about that. The closest star to us in the entire universe, and it makes no impression on the naked eye. It just lives there quietly, doing what it does, utterly indifferent to whether anything notices. Red dwarf stars typically range in mass from about 8% to about 50% of the mass of our sun. That might sound like a wide range, but what they all share across that entire spread is a particular quality of restraint. They hold back. They pace themselves in a way that no other category of star quite manages. The surface temperature of a red dwarf sits somewhere between about 2,000 and 4,000 degrees Celsius. That sounds hot, and it is by any human standard. But compared to the surface of our sun, which hovers around 5,500 degrees Celsius, it's genuinely cool. And compared to the blue-white stars at the top of the spectral sequence, which can reach temperatures of 30,000 degrees or more, a red dwarf is almost gentle. This cooler temperature is what gives them their color, a deep muted red, sometimes edging toward orange. It's not a vivid red. It's more like the color of a coal that has been burning for a very long time and is still warm, still going, but no longer trying to prove anything. The physics of what happens inside a red dwarf is somewhat different from what happens inside larger stars, and the difference matters enormously to how long they live. In a star, like our sun, energy is generated in the core through nuclear fusion, but the core doesn't mix with the outer layers of the star. The core processes its hydrogen. That hydrogen gradually becomes helium, and eventually, after a few billion years, the core begins to run low on fuel. The outer layers haven't been used. They're still full of hydrogen, but they can't get to the core to help. The sun will eventually exhaust the hydrogen in its core and begin to change, to expand, to age in the visible way that stars age. Red dwarfs work differently. Researchers have found that in many red dwarf stars, the interior is what scientists call fully convective. The material inside the star doesn't stay in layers. It circulates. It turns over. Hydrogen from the outer regions of the star is constantly being pulled down into the core, and helium and energy are constantly being brought back up and mixed through. The star essentially has access to all of its hydrogen, not just the hydrogen at the center. The result is a lifespan that is by any reasonable measure almost incomprehensible. A star like our sun will burn for roughly 10 billion years. Our sun is currently about 4.5 billion years old, meaning it is in some sense middle-aged. Red dwarf stars, depending on their mass, are expected to burn for somewhere between 1 trillion and 10 trillion years. Some estimates for the smallest red dwarfs extend even beyond that. To put that in a frame that the mind can almost reach, the current age of the universe is approximately 13.8 billion years. The smallest red dwarf stars alive today have barely begun. If they were a book, they would be on the first sentence of the first paragraph of the first page. There's something quietly extraordinary about sitting with that number. Not just as a scientific fact, but as a feeling. We tend to think of longevity as a quality of stillness, of things that don't do much, that don't change, that simply endure by virtue of not engaging with the world. But a red dwarf is not still. It is actively fusing hydrogen every moment. It is producing light and heat continuously. It is a living, ongoing process, sustained without interruption across stretches of time that dwarf everything our civilization has ever known or imagined. And it does all of this without drama, without brightness, without making itself visible from a few light years away. Scientists are still exploring what the very old age of red dwarfs might mean for the possibility of life around them. It's an open and genuinely fascinating question. A planet orbiting a red dwarf would receive far less light and heat than Earth receives from the Sun, and so to be warm enough for liquid water, it would need to orbit quite close. Much closer than Earth orbits the Sun. Close enough that some researchers wonder whether the star's gravity might lock the planet in place, keeping one face always toward the star and one face always in permanent darkness. What kind of world would that be? Half in eternal light, half in eternal night, and along the edge between them, a thin, long ribbon of perpetual twilight, where the star would sit forever on the horizon, neither rising nor setting, just present, patient, sending its dim warmth across a narrow strip of land and sea. Some scientists suggest that this twilight zone, if liquid water could persist there, if conditions aligned, might not be inhospitable to life as we understand it. The physics doesn't rule it out. Whether anything has ever actually lived in such a place is a question that remains quietly and beautifully unanswered. What we do know is that red dwarfs are not gentle in every respect. Young red dwarfs in particular can be surprisingly active. They produce flares, sudden intense bursts of energy and radiation that can be far more powerful relative to the star's normal output than the flares our own sun produces. A planet orbiting close to a young red dwarf might be bathed in radiation during these events, which could pose serious challenges to any atmosphere trying to hold together. Researchers have found that this activity tends to diminish as a red dwarf ages. The young, restless phase gives way to something much steadier, and given how long red dwarfs live, that steady phase, the long, quiet, stable phase, can last for incomprehensible lengths of time. It is something like a personality, if you can hold that word lightly. An early turbulence, a kind of unsettled youth, followed by an extraordinarily long and remarkably even middle period. A star that eventually finds its rhythm and then keeps it for trillions of years. One of the nearby red dwarfs that astronomers have studied with particular interest is a star called TRAPPIST-1, located about 40 light-years from Earth. Around this single small star, researchers confirmed the existence of 7 planets, 7 all of them, roughly Earth-sized, all of them orbiting within what scientists describe as the star's habitable zone. 3 of those planets orbit at distances where liquid water might, under the right conditions, exist on their surfaces. 7 worlds around one dim, quiet star, 40 light-years away. When this discovery was announced in 2017, it briefly changed how many scientists thought about the landscape of potentially habitable places in our galaxy. If a single red dwarf, one of hundreds of billions, could have 7 Earth-sized planets, and if red dwarfs make up the majority of all the stars in the Milky Way, then the number of potentially interesting worlds out there is not small. It is, by any reasonable extrapolation, enormous. That thought has a particular quality to it at night. Not an urgent quality, not the kind of thing that makes the mind race. More of a slow widening. The way a room seems to expand when the lights go down and your eyes adjust and you realize the walls are farther away than you thought. There is one more thing about red dwarfs that is worth carrying gently into the later hours of the night. Because they burn so slowly and because the universe is still very young, Relative to how long they will live, every red dwarf that has ever formed is still burning. Not one red dwarf has ever reached the end of its life. Not one has had time to exhaust its hydrogen and begin to change. In the entire 13.8 billion year history of the universe, no red dwarf has died. Scientists have a theoretical understanding of what will eventually happen when one does, when the hydrogen finally runs low, when the fusion begins to falter, when the star begins its long, gradual dimming. But no one has ever observed it. No evidence of it exists anywhere in the known universe. It is a chapter that hasn't been written yet, a page the cosmos hasn't turned to. In this sense, red dwarfs are still entirely in their beginning. Every single one of them. There's something in that which feels, if you let yourself settle into it, almost like a kind of companionship. You lying still in the dark of your particular night. And out there, an uncountable number of small patient fires, also at the beginning of something longer than any mind can quite hold. Both of you, in your own way, still early. The red dwarfs burn, on below the threshold of what the eye can see, too dim for unaided notice, too numerous to fully comprehend. And somewhere among them, in the quiet orbital paths around stars like Proxima and TRAPPIST-1 and hundreds of millions of others we haven't named, are worlds we have never stood on, bathed in a light that is cooler and redder and softer than the light you've known your entire life. What it would feel like to stand under that sky, with that patient dim sun hanging low and still at the horizon, is something no human has ever experienced. Whether anything else has, we don't yet know. We move on from the smallest stars, now gently, and toward the ones that burn a little brighter, the ones that in some ways feel a little more like home. There is a star you have known your entire life without ever really thinking about it as a star. It rises each morning. It moves across the sky in a slow, familiar arc. It sets, and in the hours between, it does something so ordinary that it barely registers anymore. It keeps everything alive. Every breath you've ever taken, every meal, every green thing growing outside, any window you've ever looked through. All of it running on the same quiet, continuous output from a single star that most people never bother to name in conversation because it's just the sun. But the sun is a star, a real star with a classification and a temperature and a place in the long sequence of stellar types. And what's interesting, what scientists find genuinely notable when they study it in the context of all the other stars in the galaxy, is how unremarkable it is, how thoroughly, almost perfectly average. That word might land a little strangely, average. But hold it for a moment, because there's something in it that when you let it settle, starts to feel less like a diminishment and more like a kind of quiet wonder. The sun belongs to a category of stars that astronomers classify as G-type main sequence stars, sometimes called yellow dwarfs, though the name is a little misleading on both counts. The sun is not particularly yellow. In the vacuum of space, without any atmosphere to scatter its light, it would appear almost perfectly white. The warmth we perceive in its color comes largely from the way Earth's atmosphere interacts with its light, softening and bending certain wavelengths, giving sunrises and sunsets their particular character. And it is not technically a dwarf in any dramatic sense. The word dwarf in stellar classification simply means that a star is fusing hydrogen in its core in a stable, steady way, the main sequence phase of its life. It's a dwarf in contrast to the giants and supergiants that stars can later become. Right now, the sun is doing the ordinary foundational thing, the thing it has been doing for nearly 5 billion years. The surface temperature of the Sun sits at around 5,500 degrees Celsius, warm enough to radiate light across the full visible spectrum, which is precisely why human eyes evolved to see that particular range of light. We didn't develop vision and then happen to choose a sun whose output matched it. It was the other way around. Over enormous stretches of time, life on this planet tuned itself to the specific wavelengths that the sun produces most abundantly. Our eyes are, in a very literal sense, shaped by our star. Researchers who study the co-evolution of life and light have noted how precise this match is. The peak output of the sun aligns almost exactly with the wavelengths that human vision is most sensitive to. We are, without quite knowing it, finely calibrated instruments for detecting our own star's particular kind of light. The sun has a diameter of about 1,390,000 kilometers. If it were hollow, it could contain roughly 1,300,000 Earths. These are the kinds of numbers that the mind accepts without really absorbing. They pass through comprehension without landing anywhere solid. But there's another way to hold the sun's size that might arrive a little more gently. Light traveling at its full speed takes about 8 minutes and 20 seconds to travel from the sun to Earth. It takes that same light about 4.5 seconds to travel across the full diameter of the sun itself. So the sun is not so large that light can't cross it in the span of a quiet breath. It is vast, but it is not beyond the reach of the simplest physical image, a breath, a pause, a heartbeat or two. At its core, the sun fuses approximately 600 million metric tons of hydrogen into helium every single second. 600 million tons per second. And yet, it is so large and contains so much hydrogen that this rate of consumption, sustained continuously without interruption, will take another 5 billion years or so to exhaust the hydrogen in its core. The sun is, by most reckonings, about halfway through its main sequence life. It has been burning for approximately 4.5 billion years and has roughly another 5 billion ahead of it before things begin to meaningfully change. Halfway, sitting still, burning steadily, keeping everything warm. Halfway through, something that lasts 10 billion years. What goes on inside the sun is not a simple fire in the way we usually imagine fire. It is a nuclear process, a specific sequence of reactions in which hydrogen nuclei collide and fuse under conditions of extreme pressure and temperature, forming helium nuclei and releasing energy in the process. The temperature at the sun's core is estimated at around 15 million degrees Celsius. The pressure there is so intense that matter behaves in ways that have no equivalent in ordinary experience. One of the less obvious facts about the sun's interior is how long energy takes to escape it. A photon, a single particle of light generated in the sun's core, doesn't travel directly outward and emerge into space. The interior of the sun is so dense that the photon collides with particles almost immediately after being produced, is absorbed, re-emitted in a random direction, absorbed again, re-emitted again, a process that researchers describe as a random walk, a kind of stumbling journey outward that has no direct path. Scientists estimate that a photon of energy produced in the sun's core may take anywhere from 10,000 to 100,000 years. Some estimates go considerably higher to finally work its way out to the sun's surface. And then once it reaches the surface and is released into space, it crosses the 93 million mile distance to Earth in about 8 minutes. Tens of thousands of years of wandering through the interior. 8 minutes of open space. The light warming your face on a summer afternoon set out on its journey through the sun's interior around the time early human civilizations were just beginning to form. it has been traveling inside that star slowly, without direction, for longer than writing has existed. There is something about that particular fact that tends to arrive quietly and then stay. The sun's surface, the layer visible to the eye, which astronomers call the photosphere, is not a solid surface in any conventional sense. It is a churning, moving region of plasma, the outermost layer from which light can finally escape. The temperature there drops to around 5,500 degrees Celsius, which is cool enough for certain atoms to hold together in ways they can't manage deeper inside. Across this surface, there are features that come and go on scales, ranging from hours to months. Granules, convection cells, where hotter plasma rises, cools slightly, and then sinks back down, cover the entire surface in a constantly shifting pattern, each one roughly the size of a small country. Sunspots, darker regions, where intense magnetic fields suppress the flow of energy, appear and disappear in cycles. The Sun has a magnetic cycle that runs approximately 11 years from one peak of sunspot activity to the next, and this cycle has been observed and documented for several hundred years. The Sun also has an outer atmosphere, a ghostly extended region called the corona that behaves in a way that scientists are still working to fully understand. The corona is significantly hotter than the surface below it. The surface sits at around 5,500 degrees Celsius. The corona reaches temperatures of 1 to 3 million degrees Celsius. Why the outer atmosphere would be so much hotter than the layer beneath it is a question that has puzzled solar physicists for decades, and the full answer is still being developed. It's a quiet anomaly held in the middle of the most studied star in the universe. Something unexpected, persisting in plain sight, still not entirely explained. Among the things that make the Sun relatively unusual, not unique but notable, is its solitude. Many stars, perhaps the majority, exist in systems of two or more. Binary stars, where two stars orbit around a common center of gravity, are extraordinarily common. There are triple systems, quadruple systems, complex arrangements where multiple stars circle each other in intricate gravitational choreography. Astronomers studying nearby star systems have found that single stars, like the Sun, are actually somewhat less common than multi-star systems, at least among the Sun-like and larger categories. The Sun has no stellar companion. It sits alone in its region of space, orbited only by planets, moons, asteroids, comets, smaller things, quieter things. No other star sharing its gravitational neighborhood. Researchers have speculated about what this solitude might mean for the stability of the solar system over long periods of time. A nearby stellar companion would exert gravitational influences that could perturb the orbits of the outer planets, potentially sending comets and asteroids inward in patterns that might have complicated the development of life. The Sun's isolation, by this line of thinking, may have been one of the quieter contributing factors to the relative stability that allowed life on Earth to develop and persist across billions of years. A star alone, creating stability through its aloneness. It's a thought that doesn't need to be pressed too hard to carry a certain softness with it. The light that the Sun produces doesn't arrive at Earth's surface the same way it left the Sun's surface. Earth's atmosphere intercepts it, scatters some of it, absorbs some of it. The specific wavelengths of light that the atmosphere scatters most are the shorter, higher energy wavelengths, the blue end of the visible spectrum. This is why the sky appears blue. The atmosphere is, in a sense, catching the blue light and sending it in all directions, filling the sky with it, while the longer wavelengths, the reds and oranges, pass through more directly. At sunrise and sunset, when sunlight must travel through a much greater thickness of atmosphere to reach your eyes, nearly all the shorter wavelengths have been scattered away before the light reaches you. What remains is the warm, long wavelength light, the reds, oranges, and pinks that gives those particular times of day their particular quality. Every sunrise you have ever seen was the atmosphere filtering your star's light through itself, handing you the softer end of the spectrum at the edges of the day. The sky is always interpreting the sun. We receive it translated. Psychologists who study the emotional effects of natural light have found that warm-toned light, the kind produced at the lower angles of the sun's arc, tends to be perceived as calmer and more restful than the cooler, more direct light of midday. There may be something very old in that response, something in the body that recognizes the angle of the light and understands, without being told, that the active part of the day is ending, that it is acceptable now to begin releasing the effort of being fully awake. The sun rises and sets so reliably that it has become the background of time itself for most of human history. Calendars, clocks, the very structure of how we divide a day, all of it is organized around the sun's apparent movement through the sky. And yet the sun is not moving, or rather, it is moving along with the rest of the galaxy through space, but the rising and setting that feel so fundamental are simply the result of Earth rotating on its own axis, turning toward the sun, and then away from it once every 24 hours. We experience the sun's constancy as something happening to us, arriving and departing, as if the sun chooses to come and then chooses to leave. But it stays. It is always there. It is the Earth that turns. There's a gentle shift in perception available in that fact, if you want it. The sun didn't set tonight. You turned away from it. And as you did, the stars came into view, all those other suns, all those other kinds of fires, waiting in the dark that your own rotation creates each evening. You are already moving through space, even lying still. The Earth turns you slowly through your own night. And as you drift through these quiet hours, the sun is still there on the other side of the world, doing exactly what it has done for 5 billion years. Burning steadily, going nowhere. The G-type stars, the sun and its stellar relatives, occupy a particular middle place in the sequence. Not the coolest, not the hottest, not the shortest lived, not the longest, not the most massive, not the smallest. They sit in a kind of equilibrium, burning at a pace that allows for stability over the kinds of timescales that complex things, living things, thinking things seem to need in order to develop. Whether that is coincidence or something more is a question scientists are still very carefully exploring. What is certain is that the sun has been a steady presence in this corner of the galaxy for a time that makes all of human experience seem in comparison like the briefest of pauses. And it will continue to be, for a time, equally long ahead. The stars that come next in our quiet journey tonight are a different kind, altogether, brighter, hotter, burning with an intensity that the sun never quite reaches. They are the stars that catch your eye most easily on a clear night, the ones that seem to glow with something slightly more than ordinary starlight. The white stars, the blue-white stars, the ones that burn at the higher end of what the visible spectrum can carry. They don't last as long as the sun, but while they burn, they are something to wonder at. Somewhere in the night sky, tonight, if the conditions are right, and you know where to look, there are stars that don't quite match the others. They sit among the rest of the field, surrounded by the ordinary white and faintly amber points of starlight, and they carry just barely a different quality, a coolness, a sharpness, something slightly more electric in their color, as though the light arriving from them has a little more intention behind it. These are the hotter stars, the ones that burn at temperatures the sun never reaches, and they are in a way that is difficult to describe without overstating it, genuinely beautiful to understand. The stellar classification system places stars into temperature groups, and above the Sun's category, above the warm, steady G-type stars, the sequence continues upward through two more groups before reaching the extreme end. The F-type stars sit just above the Sun, in temperature running between about 6,000 and 7,500 degrees Celsius at their surfaces. Above them, the A-type stars reach from roughly 7,500 to about 10,000 degrees, and these two groups together, the F and A stars, represent a range of stellar character that is distinct enough and common enough among the stars visible to the naked eye that they form a kind of middle ground in the story of stellar diversity. They are hotter than the Sun, they are brighter, they are whiter, and they live shorter lives, not dramatically shorter in the way that the most massive stars do, but shorter in a way that becomes meaningful when you start to think about the timescales involved. An A-type star, depending on its mass, might live for somewhere between 1 billion and a few billion years. An F-type star sits between the Sun's 10 billion-year lifespan and that shorter range. These stars have time. Not as much time as the Sun, but time enough for complexity, time enough for orbiting planets to cool and settle, time enough for scientists have quietly speculated a great many things to develop if conditions align. One of the most recognizable stars in the northern night sky belongs to this category. Sirius, the brightest star visible from most of Earth's surface, the one that sits low in the winter sky and sometimes seems to flicker with color as its light passes through layers of atmosphere, is an A-type star. It is roughly twice the mass of the Sun, about 1 3/4 times the Sun's diameter, and it burns at a surface temperature of around 10,000 degrees Celsius. It is approximately 25 times more luminous than the Sun, and it sits just under 9 light-years away. In the scale of the galaxy, that is an extraordinarily short distance. Sirius is, in cosmic terms, a neighbor. For most of recorded human history, Sirius was the brightest star in the sky, watched carefully by cultures on every inhabited continent. Ancient Egyptians aligned the orientation of certain monuments to its rising. Greek sailors used it to navigate. Its appearance on the horizon just before dawn, in the heat of summer, gave rise to the phrase, dog days, Sirius being the brightest star in the constellation Canis Major, the Great Dog. The phrase has persisted into contemporary usage long after the original astronomical observation that created it has been forgotten by most people who use it. There is something quietly layered about that. A word in everyday language carrying inside it the memory of a star. Language as a kind of fossil record, preserving the traces of what people once watched and measured and built their calendars around. The F-type stars have a particular quality that astronomers find interesting when thinking about the conditions for life. They are hot enough to be significantly more luminous than the Sun. Some F-type stars produce 2 to 7 times the Sun's energy output, which means the habitable zone around them, the orbital range where liquid water could persist on a planet's surface, sits farther out. A planet around an F-type star would need to orbit at a greater distance than Earth orbits the Sun in order to receive a similar amount of energy. But there is another consideration. Hotter stars produce more ultraviolet radiation than cooler stars, significantly more. And ultraviolet radiation, at sufficient intensity, is a complicating factor for life as we understand it. It can damage the molecular structures that living things rely on. It can strip away atmospheric layers over long periods of time. Whether the higher ultraviolet output of F-type stars makes life around them more difficult or simply different, or whether it might in some circumstances actually drive certain kinds of biological complexity, is a question researchers are still working through carefully. The honest answer is that the relationship between stellar radiation and life is not simple, and the conditions that allowed life to emerge and persist on Earth may not represent the only possible set of conditions in which something remarkable can happen. Scientists tend to hold this question with a particular kind of open-handedness. The universe has consistently surprised us by finding ways to produce complexity in places and under conditions that were previously considered unlikely. The assumption that life requires circumstances very close to our own has softened over time into something more like a working hypothesis, useful, reasonable, but not held too tightly. What makes the hotter stars visible so often among the brightest stars in our sky is partly proximity and partly sheer output. A star that produces 20 or 30 or 50 times more light than the sun can be seen from much greater distances and still appear bright. Many of the stars that ancient astronomers named and built mythology around the ones that anchor the familiar constellations are these hotter, more luminous stars. Their brightness made them natural landmarks in the sky, and their positions unchanging relative to each other across a human lifetime made them reliable guides. Researchers who study the history of astronomy have noted how the constellations that different cultures developed independently often centered on the same bright stars, not because of cultural exchange, but because those stars genuinely dominated the night sky everywhere on Earth. The same points of light caught everyone's attention. The stories told about them differed enormously, but the stars themselves were shared. There's a kind of common ground in that. Different languages, different mythologies, different ways of understanding the world, and above all of them, the same bright, hot white stars, meaning different things to different people, meaning something to everyone. The internal structure of A and F-type stars differs in subtle but meaningful ways from the Sun's interior. The Sun, as a G-type star, has a convective outer layer, a region where plasma circulates in large-scale currents, carrying energy from deeper inside toward the surface. Beneath that convective zone sits a radiative zone, where energy moves more slowly, traveling outward through absorption and re-emission, rather than through the physical movement of material. In A-type stars, this arrangement tends to reverse. The outer layers become radiative energy moves through them more directly, while convection is more limited to regions deeper inside. This affects how efficiently these stars can mix their internal material, and it has consequences for how they evolve over time and what their surfaces look like in terms of chemical composition. Some A-type stars rotate extraordinarily quickly, while the Sun rotates on its axis roughly once every 25 to 30 days. Some A-type stars rotate so fast that they complete a full rotation in less than a day. This rapid rotation causes them to bulge noticeably at their equators. They are not perfect spheres, but oblate shapes wider at the middle than from pole to pole. In the most extreme cases, an A-type star rotating at very high speed can look in cross-section less like a circle and more like a slightly flattened oval, a spinning star bulging at its waist from the speed of its own rotation. Something almost organic in that image, if you let it sit for a moment. Something that moves. Among the F and A stars, there is a subgroup that has fascinated astronomers for a long time. Stars that show unusual patterns in their spectra, where certain elements appear in concentrations far higher than expected, and others appear far lower. These stars, sometimes called chemically peculiar stars, seem to have undergone processes in their outer layers that concentrate particular elements in specific zones, creating a kind of chemical patchwork across their surfaces. Some of these stars have powerful magnetic fields that are thought to play a role in this sorting process. The magnetic structure of the star influencing where different elements settle and concentrate. As the star rotates, these chemical patches rotate with it, causing the spectrum of the star's light to change slightly and periodically as different regions come into view. It's a subtle effect, not something visible to the eye, but something measurable, patient, precise. Researchers monitoring certain of these stars over years and decades have mapped the chemical landscapes of their surfaces in fine detail, building pictures of stellar atmospheres that are genuinely complex and varied in ways that simpler models wouldn't predict. The universe, it turns out, does not settle for uniform surfaces. Even at the scale of stars, there is texture, variation, a kind of specificity that persists right down to the distribution of elements across a rotating sphere of plasma 100 light-years away. There is something that happens when you stand outside on a clear night in winter, in the northern hemisphere at least, and look toward the southern part of the sky. If the air is steady and the seeing is good, as astronomers put it, the stars don't twinkle much, they hold, and among them, the hot white stars are distinct. Sirius, already mentioned, sits low and tends to flash with color close to the horizon. But higher up, Vega, another A-type star part of the Summer Triangle and one of the brightest stars in the sky, holds a steady, cool, blue-white light that has a different quality than anything the Sun produces. Vega is about 25 light-years away. It rotates so quickly that its equatorial diameter is roughly 20% larger than its polar diameter. It is about 40 times more luminous than the Sun. And for a period of roughly 12,000 years, ending around the year 11,000 before the present, Vega served as Earth's North Pole star, the star that the Earth's rotational axis pointed toward due to a slow wobble in Earth's orientation called precession. In other words, there was a time when the star that sits fixed at the center of the northern sky, the star sailors and travelers used to find north, was not Polaris, as it is now, but Vega. Brilliant, fast-rotating, blue-white Vega. The sky we navigate by is not permanent. Even the North Star changes on a long enough time scale. The whole sky wheels slowly, the pole tracing a wide circle among the stars over a period of roughly 26,000 years, and different stars take their turn at the center. Polaris will eventually drift away from that position too, and Vega will return to it. Not soon, in any human sense, but eventually. The perception of color in starlight is something worth holding gently for a moment because it involves the eye in a way that is easy to overlook. Human color vision depends on specialized cells in the retina called cone cells, which are sensitive to different ranges of wavelengths. But cone cells require a certain minimum level of light to function. In very low light conditions, the eye shifts to relying primarily on rod cells more sensitive, but not capable of distinguishing color. This is why, under a truly dark sky, most stars appear simply white or faintly silver, even though they are in physical reality carrying distinct colors. To actually perceive the blue of a hot star or the orange of a cooler one, you need a star that is bright enough to activate the cone cells, or you need optical aid, which gathers more light than the eye alone. Binoculars, even a simple pair, can make the color differences between stars suddenly and beautifully apparent in a way that the naked eye, operating at the edge of its sensitivity, cannot easily achieve. Researchers who study visual perception have noted that this threshold effect, the shift between rod and cone vision, is one of the reasons the night sky can feel both familiar and slightly strange at the same time. You are seeing it with a different visual system than the one you use during the day. The night eye is older in evolutionary terms, more sensitive to movement and to light and dark, less capable of fine color discrimination, more attuned in some fundamental way, to the simple presence or absence of light. Looking at stars is, in a quiet sense, looking with the older part of yourself. The F and A stars burn through their hydrogen more quickly than the sun, not recklessly, not at the pace of the great blue giants, but steadily faster, with more energy going out in every moment. And when their core hydrogen begins to run low, they will change, they will expand, they will cool slightly at their surfaces and grow in size, becoming something different from what they are now. But that change is still far in the future for most of the stars in this category. Right now, they are in the long, stable, burning middle of their lives, holding steady, bright and white and slightly cooler than the most extreme things the universe produces, but still so much hotter than anything on Earth that the comparison barely holds shape. The stars beyond them, in the sequence, the ones that genuinely earn the word extreme, are waiting a little farther along in this quiet journey. Stars so massive and so bright that they change the neighborhoods of space around them. Stars that live fast and briefly and leave evidence of themselves that persists long after they are gone. But there's no need to move quickly. The night is still early in its way, and the slow drift from one kind of star to the next has a rhythm that is worth staying inside for a little longer. Aging for a star is not a sudden thing. It doesn't happen in a moment or even across a recognizable span of time by any human measure. It happens across hundreds of millions of years, a slow, almost imperceptible shift in the internal balance that has kept the star steady for so long. And then gradually, the outward appearance begins to change. The star grows. It expands. It becomes, in the most literal sense, something larger than it was. This is how giants are made. Not through force, not through collision or catastrophe, but through the quiet exhaustion of what was always going to run out eventually. It is, in its own way, one of the more peaceful transformations the universe produces. When a star like the Sun, or a star somewhat more massive, begins to deplete the hydrogen in its core, something fundamental shifts in the balance of forces that have defined it. The core, now increasingly composed of helium rather than hydrogen, can no longer sustain fusion at the same rate. The outward pressure that has been holding gravity at bay begins to weaken, and the core starts to contract. It compresses inward under its own weight, and as it does, it heats up. This additional heat doesn't stay in the core. It radiates outward into the layer of hydrogen that still surrounds the core, the shell of unburned fuel that has been sitting there all along, untouched, because the star never needed it before. Now it does. The heat from the contracting core ignites this shell, and hydrogen fusion begins in a ring around the core rather than at the center of the star. Shell fusion, as this process is called, produces energy at a higher rate than core fusion did. And all of that extra energy has to go somewhere. It pushes outward into the star's outer layers, and those layers respond by expanding. Slowly, over many millions of years, the star swells. The surface, as it spreads outward and thins, cools. And as it cools, it shifts in color from the white or pale yellow of a main sequence star toward the warmer, deeper tones of orange and red. The star is becoming a giant. It is becoming specifically what astronomers call a red giant, or depending on its mass and the stage of its evolution, an orange subgiant. Arcturus is a star worth spending a quiet moment with. It hangs in the northern sky, visible for much of the year, and it carries a color that is genuinely different from most of the stars around it, a warm, unmistakable orange that has caught the attention of sky watchers for thousands of years. Arcturus is the brightest star in the northern celestial hemisphere, and the fourth brightest in the entire night sky. It is classified as a K-type giant, an orange giant in the more common language, sitting at a surface temperature of roughly 4,300 degrees Celsius, noticeably cooler than the Sun. Its diameter is about 25 times larger than the Sun's. If you placed Arcturus where the Sun is, its surface would extend roughly a third of the way to the orbit of Mercury. And yet, despite its size, Arcturus is only about 1.5 times the mass of the Sun. It has expanded into something enormous, but without adding mass, purely by redistributing what it already had, spreading itself across a much greater volume of space. Researchers studying Arcturus have found something additionally interesting about its motion through the galaxy. It is traveling on a distinctly different orbital path around the center of the Milky Way than most stars in its neighborhood, moving at a different angle and speed, suggesting that it may have originally formed in a smaller galaxy that was absorbed by the Milky Way long ago. The stars from that ancient consumed galaxy still travel together in loose groups on tilted orbits that carry them through the galactic disk on paths that stand apart from the general flow. Arcturus may be a traveler from somewhere else, a visitor in the deep time sense, still moving on the trajectory it inherited from a galaxy that no longer exists. That thought has a particular quality of distance to it, gentle but vast. The red giant phase represents one of the longer-lived stages in a star's later life, but it is not static. Stars in this phase can undergo complex changes in their interiors as different nuclear processes come and go. Once the hydrogen shell has burned for long enough and the helium core has grown dense and hot enough, conditions can eventually reach the point where helium itself begins to fuse. Helium fusion, the process by which helium nuclei combine to form carbon and oxygen, requires much higher temperatures and pressures than hydrogen fusion. The onset of helium fusion in a low to intermediate mass star can happen relatively suddenly in an event that astrophysicists call the helium flash. In the space of a few minutes, the rate of helium fusion in the core can increase dramatically before the core expands enough to stabilize the process. No one has ever directly observed a helium flash from outside a star. The event happens deep in the core, and the energy it releases is absorbed by the star's outer layers before any light from it reaches the surface. But theoretical models and computer simulations have allowed researchers to map out what is happening in those internal layers with considerable confidence, and the picture that emerges is of an extraordinarily rapid release of energy, equivalent in some models to the total output of the entire Milky Way galaxy, sustained for a brief period, hidden entirely within the star, invisible from outside, felt only indirectly in the slow, subsequent adjustments of the star's structure. A transformation of extraordinary intensity, happening in total silence, invisible to any observer. There is something in that which the mind holds differently than a visible explosion, something more interior, more private. Betelgeuse is perhaps the most discussed red giant, or more precisely red supergiant, in contemporary astronomy, and it earns its attention. It sits at the left shoulder of the constellation Orion, a constellation so widely recognized that it appears in the mythology and navigation traditions of cultures on every inhabited continent. Betelgeuse is one of the largest stars visible to the naked eye. Estimates of its diameter vary due to the complexity of measuring a star whose outer layers are diffuse and irregular, but most place it somewhere between 700 and 900 times the diameter of the Sun. If Betelgeuse were placed at the center of our solar system, its surface would extend to somewhere around the orbit of Jupiter. The star is a semi-regular variable. It pulsates, expanding and contracting on timescales ranging from roughly 400 to over 2,000 days, brightening and dimming as it does. This variability has been noticed for centuries, though the underlying physical reasons for it have only been worked out relatively recently. Between late 2019 and early 2020, Betelgeuse underwent what became known as the Great Dimming, a period during which it faded to roughly 60% of its usual brightness, sparking considerable public interest and some premature speculation about what it might signal. Researchers subsequently determined that the dimming was most likely caused by a combination of factors: a large, cool, convective cell on the star's surface, essentially a giant cool patch, like a vast sunspot, but on an incomparably larger scale, combined with dust that condensed from material the star had ejected into the space around it, temporarily blocking some of its light from reaching Earth. The star recovered. It brightened again, and the episode offered scientists an unusually clear window into the behavior of a star whose surface is active and turbulent in ways that are difficult to study directly. What is certain is that Betelgeuse is nearing the end of its life, not imminently on any human timescale, but in astronomical terms, it is in its final phase. At some point in the relatively near stellar future, it will exhaust its remaining nuclear fuel and collapse, producing a supernova. When that happens, it will be briefly visible in daylight from Earth. Briefly in this context means somewhere between a few weeks and a few months. No one knows when. Scientists are still exploring the timeline. Betelgeuse has been near the end for a long time by human reckoning, and it may remain so for another 100,000 years, or it may have already undergone its collapse. The light simply hasn't reached us yet. At roughly 700 light-years away, we would not see the supernova until 700 years after it actually occurred. We are always watching the past. Even the most dramatic events in the sky reach us with a delay we can't quite feel, but can't quite forget either. The coolest giants, the K and M-type giants, the orange and red ones, have surfaces that are interesting to astronomers for reasons beyond their temperature. At these cooler temperatures, certain molecules can form in the star's outer atmosphere that simply don't exist in hotter stars. Titanium oxide is one of them. It produces distinctive absorption features in the spectra of cool giant stars that serve as reliable markers of their temperature range. Some cool giants also develop complex chemistry in their outer layers and their stellar winds, producing dust grains that drift outward into the space around them. This stellar dust, tiny particles of carbon, silicates, and other compounds, joins the interstellar medium, the diffuse material that fills the spaces between stars. Over enormous timescales, this dust accumulates and mixes with gas, and these clouds eventually become the raw material from which new stars and planets form. The atoms in your body passed through stars before they became part of you. Most of them were forged in stellar interiors and released into space when those stars ended their lives. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it arrived here through a long chain of stellar processes, including the slow, expanding deaths of giant stars that scattered their material into the galaxy over billions of years. Researchers often note this as one of the more striking aspects of stellar science, not as a metaphor, but as a literal account of physical history. The elements that make up living things were produced in stars and distributed by their deaths. The connection is not poetic. It is chemical. It is measurable. It is simply true. And there is something about knowing that in the quiet of a late night that settles differently than most facts do. Not like information arriving from outside, but like something already known, finally being named. Giant stars, particularly the most luminous red supergiants, lose mass continuously through powerful stellar winds. The sun has a solar wind, a constant stream of charged particles flowing outward through the solar system, but it is relatively gentle. Red supergiants like Betelgeuse lose material at rates that are millions of times higher. They are actively shedding their outer layers into space, surrounding themselves with expanding shells and clouds of gas and dust that can extend for light years in every direction. This mass loss is itself a form of giving back. The material that was assembled over millions of years inside the star, processed through nuclear reactions, transformed from hydrogen into helium, into carbon and oxygen and heavier elements, is now being released. It joins the galaxy's general circulation of matter. It becomes available again. The giant phase of a star's life is in this sense a time of increasing generosity. The star takes up more space, shines more brightly in some respects, and simultaneously begins to release what it has been holding. There is a particular kind of beauty in that sequence if you let yourself stay with it. The expansion and the opening happening together. Orange and red giant stars are scattered throughout the night sky, and once you know their color, you begin to notice them not as anomalies, but as presences. Aldebaran in Taurus is a red giant with a diameter about 44 times that of the Sun. Pollux in Gemini is an orange giant, the nearest giant star to our solar system at about 34 light years. Gamma Crucis, visible from the southern hemisphere, marks the top of the Southern Cross and is a red giant as well. They are everywhere in the catalogue of bright stars, aging, expanding, cooling at their surfaces, while burning at new sites in their interiors, living out a phase that is for each of them the longest, and in some ways the most complex chapter of their lives. The Sun will be here eventually, not for another 5 billion years or so, but the trajectory is already written in the physics. It will expand, cool at its surface, and grow to perhaps 100 to 200 times its current size. Whether Earth's orbit will remain outside the Sun's expanded surface or be engulfed by it is something that researchers are still refining. The answer depends on details of orbital dynamics and mass loss that are genuinely uncertain, but the general shape of what comes is understood. For now, the Sun is still early, still burning at its core, still stable, still middle-aged in the long story of what it is. The giant phase is not now. It is a future so distant that no current unit of human time quite captures it. And the stars above you tonight that are already in that phase, the orange and red giants, glowing quietly in the field of stars, they are simply further along, older, wider, in the expansive, generous middle of their ending. There are stars ahead in this journey that never reach that quiet expansion at all. Stars that live so briefly and burn so intensely that they don't have time to grow into giants. Stars that consume themselves quickly, brilliantly, and leave behind something entirely different from what they were. The sky holds them too, and they are worth finding gently when you're ready. There are things in the universe that are simply too large for the imagination to hold comfortably, not in a frightening way, more in the way that certain landscapes, a wide ocean, a mountain range, stretching beyond the edge of vision, produce a particular kind of quieting in the mind. The scale exceeds what the brain can model with any precision, and so the brain releases the attempt. It stops trying to measure and simply receives. Something in that release feels unexpectedly like rest. The blue giants and blue supergiants are that kind of thing. At the upper end of the stellar classification sequence, in the categories, astronomers label O and B sit stars that are genuinely difficult to describe in terms that carry their full meaning. They are massive, not in the way that the Sun is massive, which is already beyond ordinary comprehension, but in a way that makes the Sun look modest by comparison. The most massive stars known to science carry somewhere between 50 and over 200 times the mass of the Sun packed into a single object. Their surface temperatures run from around 10,000 degrees Celsius at the lower end of the B category up to 50,000 degrees or more for the hottest O-type stars. At those temperatures, the dominant output is not visible light. It is ultraviolet radiation, wavelengths shorter than violet beyond what human eyes can detect. The light that reaches your eye from a blue supergiant is in a sense only part of what it is producing. The majority of its energy is radiating in wavelengths you cannot see, flooding the space around it with radiation that can ionize the gas for hundreds of light years in every direction. The regions of ionized gas that surround clusters of hot blue stars are among the most visually striking structures in the galaxy. Luminous clouds, called emission nebulae, where the gas has absorbed the ultraviolet light from nearby massive stars and is re-emitting it as visible light, often in the characteristic red of ionized hydrogen. The Orion Nebula, visible as a faint smudge below the three belt stars of Orion on a clear night, is one of these regions. The blue stars at its center are responsible for making it visible. They are illuminating the cloud from within. The luminosity of the most massive blue stars is by any reasonable measure extraordinary. Some O-type supergiants outshine the Sun by factors of several 100,000 to over 1 million. A single star producing 1 million times the light of the Sun, sitting alone in space, radiating that energy in every direction continuously. One of the most luminous stars known in our galaxy is a blue hypergiant, an extreme category even within the already extreme blue supergiant class called Eta Carinae. It sits roughly 7,500 light-years away in a region of intense star formation in the southern Milky Way. Its total luminosity is estimated at somewhere between 4 and 5 million times that of the Sun. The system is actually a binary two massive stars orbiting each other, but the primary component dominates so completely that it is often discussed as a single object. In the 1840s, Eta Carinae underwent a massive eruption, not a supernova, but something called a great eruption, during which it briefly became the second brightest star in the night sky, despite being thousands of light-years away. It ejected an enormous quantity of mass into the space around it, forming the expanding cloud of gas and dust that now surrounds it, known as the Homunculus Nebula. That nebula is still expanding today, and its structure has been studied in considerable detail, revealing a complex bipolar shape, two lobes pushing outward in opposite directions from the star's equatorial plane. Eta Carinae is considered one of the most likely candidates for a future supernova in our galaxy, though the timing, as with Betelgeuse, remains genuinely uncertain. It may undergo its final collapse within the next 100,000 years or sooner. When it does, it will be visible from Earth, possibly in daylight, and the event will be studied with every instrument available to astronomy at that time. But that is still the future. Right now, Eta Carinae simply exists, burning at a rate that is difficult to hold in the mind, pouring energy into a small patch of the galaxy with a persistence that has been going on uninterrupted for the millions of years it has already lived. The lifespan of a massive blue star is one of the more striking inversions in stellar science. Where the smallest red dwarfs will burn for trillions of years, the most massive blue stars may exhaust their hydrogen fuel in as little as a few million years. Some of the most extreme examples live for only 1 to 3 million years before their cores begin to fail. In the context of the galaxy, which is roughly 13 billion years old, a few million years is genuinely brief. The most massive stars that formed early in the galaxy's history are long gone. They burned through their fuel and ended their lives before the solar system even began to form. The blue supergiants visible in the sky today are in a sense recent. They formed relatively recently in galactic time from clouds of gas and dust that had already been enriched by the deaths of earlier stellar generations. Researchers who study star formation have noted that massive stars are also relatively rare. The process by which stars form tends to produce many more low-mass stars than high-mass ones. The initial mass function, as it is technically called, falls steeply toward higher masses. For every star like Eta Carinae or Rigel, there are thousands or tens of thousands of smaller, less luminous stars. The massive stars are conspicuous because of their brightness, but they are deeply outnumbered. There's something in that proportion that invites a quiet thought. The rarest things in the sky are often the most visible. What you notice most easily is not necessarily what is most common. The sky in this way is a slight illusion, a display weighted toward the spectacular, while the quiet majority burns on unseen in the background. Rigel is the brightest star in Orion and one of the brightest in the entire night sky. It appears in the lower right of the constellation, the left foot of the hunter figure in the traditional reading, and it carries a blue-white color that is apparent even to the naked eye under good conditions. Rigel is a blue supergiant classified as a B-type star sitting at a surface temperature of around 12,000 degrees Celsius. Its luminosity is estimated at approximately 120,000 times that of the Sun. Its distance from Earth is roughly 860 light-years, and at that distance, shining with that luminosity, it is still one of the brightest objects in the night sky. The arithmetic of that is worth sitting with for a moment. 860 light-years away, still brilliant. Rigel also has companion stars, a gravitationally bound system, rather than a solitary star. The companions are much fainter and much harder to observe, but they are there orbiting in the extended gravitational field of the supergiant. Multi-star systems involving massive blue stars are actually quite common. The gravitational dynamics of dense star-forming regions seem to favor the formation of binaries and multiples, particularly at the high-mass end. The behavior of two massive stars in close orbit around each other can produce effects that neither would produce alone: enhanced mass transfer, mutual tidal distortion, and in some cases, when both stars eventually reach the ends of their lives, a sequence of supernovae that can send remnants hurtling through the galaxy at remarkable speeds. Some of the fastest-moving stars, known called hypervelocity stars, are thought to have been flung outward by exactly this kind of double-star death, the second explosion sending its companion racing away from the site at hundreds of kilometers per second. Stars that were once bound to each other, separated by the violence of one of them ending. Traveling outward alone through the galaxy, still carrying in their motion the signature of what they once shared. The internal structure of a massive blue star processes nuclear fuel in a sequence that moves through elements in a way that lower mass stars never reach. While smaller stars fuse hydrogen and then helium, the cores of massive stars are hot and dense enough to continue fusing past helium into carbon, then neon, then oxygen, then silicon. Each stage is shorter than the last, because each successive fuel releases less energy per unit mass than the one before it. Hydrogen burning can last millions of years, helium burning a few 100,000, carbon burning perhaps a few thousand years, neon burning roughly a year, oxygen burning months, silicon burning the final stage before the core reaches a composition of iron which cannot release energy through fusion lasts in the most massive stars only a matter of days. Days, after millions of years of burning hydrogen, the final stages of nuclear processing in a massive star's core can flash through in what is by comparison an eye blink. Iron is the terminus. When the core of a massive star becomes predominantly iron, fusion stops. Iron is the most stable nucleus fusing. It absorbs energy rather than releasing it. The outward pressure generated by nuclear processes collapses, and without it, nothing is holding back the gravity that has been pressing inward all along. The core falls. In less than a second, it collapses from something roughly the size of Earth to something roughly the size of a city. And the energy released in that collapse is incomprehensible, greater than the total energy output of the Sun across its entire 10 billion year lifetime, released in a fraction of a second. The outer layers of the star falling inward toward the collapsed core rebound from it in a shock wave that blows them outward at a significant fraction of the speed of light. A supernova. The light from this event, if you were positioned at a safe distance to observe, it would outshine entire galaxies for weeks. A single dying star, briefly brighter than 100 billion others. What remains after a supernova depends on how massive the original star was. This is something the next stretch of the night will move into more slowly and carefully, because what remains is its own kind of story, dense, strange, and worth approaching gently. But there is something worth staying with just here before moving on. The elements produced in the cores of massive stars, the carbon, the oxygen, the silicon, the iron, and in the supernova explosion itself, many of the heavier elements that cannot be built any other way are scattered into the galaxy by the explosion. They travel outward into the interstellar medium, mixing with hydrogen and helium, seeding the raw material of future star systems with the complexity that only the deaths of massive stars can provide. The heavier elements in the universe, everything beyond iron, including the gold, in any jewelry you might own. The uranium that powers certain energy plants. The iodine your body uses for thyroid function were forged in the extreme conditions of supernova explosions and other violent stellar events. They were distributed into space by those explosions, incorporated into new clouds of gas and dust, eventually drawn together into new stars and the planets that formed around them. Heavy things made in intensity, released in finality, drifting for millions of years, ending up here. Researchers who study nucleosynthesis, the science of how atomic nuclei are built inside stars and stellar explosions, have traced these elemental origins in considerable detail. The periodic table is in a real sense a record of stellar history. Each element carries in its structure the memory of the conditions that produced it. Some were made in the quiet cores of long-lived stars. Others required the brief, extraordinary pressure of a dying massive star. Others still were forged in even more extreme events, the merging of neutron stars, the endpoints of the most massive stellar lives, which will come into the story a little later. For now, the blue supergiants burn on in the night sky above you. Rigel, cold and brilliant. Eta Carinae, hidden behind its own expelled shell, raging quietly in the southern sky. And countless others unnamed to most people who have ever looked up, doing what they do with complete indifference to whether it is noticed or understood. They are burning the shortest chapters of the longest story the universe tells. And when they are done, they leave behind things that last. What they leave behind, the dense, strange, silent objects that remain after the largest fires, is where we find ourselves drifting next. After the brightness, there is a different kind of presence. Not darkness exactly, not absence, but something quieter than what came before, a cooling, a settling, a long and patient diminishing that has its own particular character. When a star, like the Sun, reaches the end of its active life, what it leaves behind is not nothing. It is something small and dense, and still faintly warm, and it will remain that way for longer than the current age of the universe has yet existed. These objects are called white dwarfs, and they are in the most literal sense what most stars become when they are finished. The path to becoming a white dwarf begins in the red giant phase, in that long expanded shell-burning stage that lower and intermediate mass stars pass through after their core hydrogen is exhausted. As a red giant ages further, the helium shell burning becomes unstable, pulsing in thermal cycles that cause the star's outer layers to be pushed progressively outward. Over thousands of years, these outer layers drift away from the star, entirely forming an expanding shell of gas and dust that moves outward into the surrounding space. This shell is called a planetary nebula, a name that has nothing to do with planets, and was assigned in the early days of telescopic astronomy, when these objects seen through small telescopes vaguely resembled the round disk of a planet. The name persisted. The resemblance is superficial. What a planetary nebula actually is a star's outermost layers released slowly and continuously illuminated by the hot core now exposed at the center. That exposed core, stripped of its outer envelope, no longer able to sustain fusion, compressed by gravity into a sphere roughly the size of Earth, is the white dwarf. Its initial temperature immediately after the nebula clears can be extraordinarily high. Some newly formed white dwarfs have surface temperatures above 100,000 degrees Celsius. At those temperatures, they emit strongly in the ultraviolet range, and they are responsible for ionizing the surrounding planetary nebula, causing it to glow. The nebula and the white dwarf at its center are for a time in a relationship, the star's remnant still energizing the beautiful shell it shed during its ending. Planetary nebulae are among the most visually striking objects in astronomy. Their shapes are varied and complex. Some are nearly spherical. Others form butterfly or hourglass shapes. Some have multiple concentric rings. Others trail long filaments of material into the surrounding space. The variety arises from the complexity of the mass loss process and the influence of magnetic field's rotation, and in many cases, binary companion stars that shape how the material is ejected. The Ring Nebula in the constellation Lyra is one of the most studied examples. It appears in telescope images as a softly glowing ring of gas, blue-green at the center, fading to orange and red at the edges, with the white dwarf faintly visible as a point of light at the very center. It sits roughly 2,300 light-years away and is expanding outward at a speed of roughly 20 kilometers per second. In a few tens of thousands of years, it will have dispersed enough to become invisible, the gas thinning into the interstellar medium, the white dwarf left alone in the dark. The Helix Nebula, sometimes called the Eye of God, in popular descriptions, a name that captures something of its appearance but not its nature, is the nearest known planetary nebula to Earth, sitting about 650 light-years away. It spans roughly 2.5 light-years across. Its central white dwarf has a surface temperature of around 120,000 degrees Celsius and is thought to be sending out a powerful wind of particles, even now interacting with the ejected shell in ways that researchers are still working through. These nebulae are transient. They exist for tens of thousands of years, a brief window in astronomical time before dispersing. The white dwarf they frame will outlast them by almost unimaginable margins. A white dwarf is supported against further gravitational collapse not by nuclear fusion that has ended, but by a quantum mechanical effect called electron degeneracy pressure. In ordinary matter, electrons occupy distinct energy states, and the Pauli exclusion principle, a fundamental rule of quantum mechanics, prevents two electrons from occupying the same state simultaneously. When matter is compressed to white dwarf densities, the electrons are packed so tightly that this exclusion pressure becomes the dominant force resisting further compression. It is a pressure that does not depend on temperature. It does not diminish as the star cools. This is what makes white dwarfs so remarkably stable as cooling objects. They are not burning, they are not generating energy through any active process. They are simply radiating away the heat they accumulated during their active lives slowly over trillions of years, supported in their compressed state by a purely quantum mechanical resistance to further collapse. The density of a white dwarf is difficult to hold in an intuitive frame. A typical white dwarf, roughly the mass of the Sun, compressed into roughly the size of Earth, has an average density of around 1 million grams per cubic centimeter. A teaspoon of white dwarf material, were you able to somehow scoop it up, would weigh somewhere in the range of 5 metric tons. Not because the atoms themselves are different, they are the same atoms found anywhere, but because the space between them has been so thoroughly eliminated that matter is packed at a density that has no analog in everyday experience. And yet white dwarfs are not the densest things the universe produces. They sit in an interesting middle position, denser than anything on Earth, less dense than what comes after them in the sequence of stellar endings. The cooling of a white dwarf is not a rapid process. It follows the laws of thermal radiation. A hot object radiates energy proportional to the fourth power of its temperature, meaning that as it cools, it radiates more slowly, and the cooling itself decelerates. A white dwarf that forms at 100,000 degrees will cool to temperatures similar to the Sun's surface over a period of hundreds of millions of years. To cool further down to the temperatures of a red dwarf, for example, would take billions of years more. Theoretical astrophysicists have calculated that white dwarfs cool slowly enough that even the oldest ones in the universe, those that formed from the first generation of intermediate mass stars more than 10 billion years ago, are still warm. They have cooled considerably from their initial temperatures, but they have not had enough time to reach very low temperatures. The universe is not old enough yet for its white dwarfs to have truly gone cold. There is a prediction, which no one has yet been able to observe, that given enough time, far more time than the universe has currently existed, white dwarfs will cool to such low temperatures that the carbon and oxygen in their interiors will crystallize. The interior of a sufficiently old and cool white dwarf would be, in a physical sense, a giant crystal, the nuclei locked into a regular lattice, a structure resembling diamond, but at densities and pressures incomparably greater than any diamond formed on Earth. Some researchers believe this crystallization process has already begun in the oldest, coolest white dwarfs currently observable. There is observational evidence, a subtle clustering in the brightness and temperature distribution of old white dwarfs, that something is releasing extra heat during a particular phase of their cooling, consistent with what would be expected during crystallization. The interior of an ancient star becoming by degrees a crystal. It is the kind of fact that arrives quietly and then stays. The mass of a white dwarf is constrained by a fundamental physical limit. In the early 20th century, a young astrophysicist named Subramanian Chandrasekhar, working on a ship voyage from India to England at the age of 19, calculated that there is a maximum mass above which electron degeneracy pressure cannot support a collapsed stellar core. That limit is approximately 1 4/10 times the mass of the Sun. A white dwarf, more massive than this limit, the Chandrasekhar limit, as it is now universally known, cannot hold itself together through degeneracy pressure alone. If a white dwarf in a binary system accumulates material from a companion star gaining mass over time and approaches or exceeds this limit, it can undergo a thermonuclear explosion, a type of supernova called a Type 1. A supernova different in origin from the core collapse supernova that end massive blue stars. Type 1, as supernovae, are among the most important tools in cosmology because they occur with a remarkably consistent intrinsic brightness. By comparing how bright they appear to how bright they actually are, astronomers can measure vast distances across the universe. It was observations of Type 1, a supernovae, that in the late 1990s led to the discovery that the expansion of the universe is accelerating, a finding that earned the Nobel Prize in Physics in 2011 and introduced the concept of dark energy into mainstream cosmological discussion. A white dwarf cooling alone in the dark, or in the right circumstances, dramatically reversing its quiet trajectory and briefly outshining a galaxy. The same object, two entirely different futures, depending entirely on whether it has company. The Sun will become a white dwarf. This is not a speculation, it is a straightforward extrapolation from the physics of its mass and composition. In roughly 5 billion years, it will exhaust its core hydrogen, expand into a red giant shed, its outer layers as a planetary nebula, and the exposed remnant at its center will be a white dwarf roughly half the Sun's current mass, compressed to roughly the size of Earth. What happens to the inner planets during the red giant phase, whether Earth survives or is engulfed, is still an open question that depends on the precise details of how much mass the Sun loses and how orbital distances respond to that mass loss. But regardless of what happens to the planets, the white dwarf that remains will be small, dense, and cooling very slowly in a solar system that is much quieter and emptier than the one we inhabit now. That white dwarf will persist. It will still be there, warmer than the background temperature of space, but growing slowly less distinguishable from it after timescales that no human calendar system has meaningful words for. It will outlast the galaxy in its current form. It will outlast the era of star formation. It will persist through the long dark period that cosmologists sometimes call the degenerate era of the universe, when active stars have largely ceased to exist, and the cosmos is populated mostly by the cooling remnants of what they once were. In that distant future, white dwarfs will be among the most common objects in the universe. A galaxy of slowly cooling embers, each one carrying in its crystalline interior the compressed memory of a star that once burned, once lit the space around it, once perhaps warmed a planet. There is something in the white dwarf's nature that has a particular resonance at this hour, in this quietness. The idea of something that was once intensely active, fusing hydrogen, expanding, shining now, simply cooling, no longer generating, no longer struggling to maintain balance against gravity, simply present, releasing heat gradually into the surrounding dark, held together by quantum rules that don't ask anything of the object they support. No effort, just the long, slow exhale of warmth into space. Researchers who study the psychology of rest have noted that the transition into sleep shares certain qualities with this kind of state, change a shift from active generation to passive release, from effort to the absence of effort, from the maintenance of complex internal processes to a simpler, quieter mode of being. The brain, moving towards sleep, reduces its metabolic rate, lowers its temperature, slightly releases the active management of the waking state and settles into something slower and more self-sustaining. Not the same thing, obviously. Nothing so small as a night's sleep maps cleanly onto the cooling of a dead star across trillions of years. But the direction of the movement is similar, toward stillness, toward the patient release of what has been held. The white dwarfs cool on out there in the enormous quiet between things, and the universe is patient enough to wait for them to finish. What is stranger than a white dwarf? Stranger in its physics, stranger in its behavior, stranger in the questions it raises about the nature of matter itself, is what remains when stars more massive than the white dwarf threshold reach their endings. Objects so compressed that the very concept of ordinary matter no longer applies in any familiar way, spinning in the dark, sending signals across light years, pressing against the boundaries of what physics can describe with confidence. Somewhere in the galaxy tonight, something is spinning. Not the slow, dignified rotation of a planet or the gradual turning of a star across weeks and months. Something spinning, the way a top spins when it has just been released, fast, almost incomprehensibly fast, completing full rotations in fractions of a second, sometimes dozens of times per second, sometimes hundreds of times. A ball of matter, roughly the size of a city, the compressed remnant of something that was once a star, far more massive than the sun, rotating so rapidly that its surface moves at a significant fraction of the speed of light. And as it spins, it sends out a beam, a narrow, sweeping pulse of radio waves, sometimes also X-rays and gamma rays, rotating with the star like the beam of a lighthouse. If Earth happens to lie in the path of that beam, we receive it. A click, a pulse, a signal so precise and so regular that when it was first detected in 1967, the scientists who found it genuinely considered briefly and seriously whether it might be artificial, whether something was sending it deliberately. They nicknamed the signal LGM-1, Little Green Men, not because they believed it, but because they didn't yet know what else to call something, that regular something, that patient, something that arrived on schedule with a reliability that no natural process they knew of could produce. It was, of course, natural, extraordinarily natural. It was a pulsar, a rapidly rotating neutron star, and its discovery opened a window into one of the strangest categories of object the universe contains. A neutron star forms when a massive star, typically one between about 8 and 20 times the mass of the Sun, undergoes core collapse at the end of its life. The iron core, as described earlier in this journey, collapses in less than a second. But for stars in this mass range, the collapse does not proceed all the way to a black hole. Instead, it is halted by a different quantum mechanical effect, neutron degeneracy pressure, analogous to the electron degeneracy pressure that supports white dwarfs, but operating at far greater densities. In the collapsed core, the pressure is so extreme that electrons and protons are forced together, combining to form neutrons. The entire core becomes, in essence, a single enormous atomic nucleus, a sphere of neutrons packed at nuclear density, roughly 10 to 13 kilometers in diameter, containing somewhere between 1 and 3 times the mass of the Sun. 10 to 13 kilometers, the size of a city, the mass of a star. The density of a neutron star is by any earthly measure simply outside the range of intuition. A single teaspoon of neutron star material would weigh somewhere around 400 million metric tons. The density at the core of a neutron star approaches and may exceed the density of an atomic nucleus, the kind of matter found at the center of atoms, but sustained across an object kilometers wide, rather than femtometers across. Researchers are still working to understand what matter actually does at those central densities because the physics of that regime lies at the boundary of what current theory can describe with confidence. Some models suggest that at the very center of a neutron star, the neutrons themselves may dissolve into their constituent quarks, the fundamental particles that make up protons and neutrons, forming what is sometimes called quark matter. This is still theoretical territory, genuinely open, genuinely uncertain. The interior of a neutron star is one of the places in the universe where the known laws of physics reach their limits and begin to blur into questions that do not yet have answers. The newly formed neutron star inherits the angular momentum of the collapsing core. And because angular momentum is conserved, the same physical principle that causes a spinning ice skater to speed up when pulling their arms inward, the dramatic reduction in size from a stellar core to a neutron star causes the rotation rate to increase enormously. A stellar core that was rotating slowly becomes, upon collapse, a neutron star spinning many times per second. The magnetic field is also concentrated in this collapse. A star that had an ordinary stellar magnetic field, already enormous by any planetary standard, sees that field compressed into an object billions of times smaller. The result is a magnetic field at the neutron star's surface that can be 1 trillion times stronger than Earth's magnetic field. This extraordinary magnetic field, combined with the rapid rotation, is what produces the pulsar effect. Charged particles are accelerated along the magnetic field lines near the magnetic poles, and they emit radiation in narrow beams, radio waves, sometimes X-rays, sometimes gamma rays, pointed outward along the magnetic axis. Because the magnetic axis is typically tilted relative to the rotation axis, these beams sweep around as the star rotates, like the beam of a lighthouse sweeping across the sea. If Earth happens to lie in the plane of that sweep, we receive the beam once per rotation. A pulse. Regular, reliable, precise. The precision of pulsar timing is in some cases remarkable enough to be useful as a scientific instrument in its own right. The most stable pulsars, a subgroup called millisecond pulsars, which have been spun up to extremely high rotation rates by accreting material from a companion star, keep time with a regularity that rivals or exceeds atomic clocks. Researchers have used networks of millisecond pulsars distributed across the galaxy as a kind of gravitational wave detector, monitoring tiny variations in pulse arrival times caused by gravitational waves passing through the space between the pulsars and Earth. The most stable spinning remnants of stellar death used as instruments to measure ripples in the fabric of space-time. The universe, in this way, occasionally provides its own tools. Jocelyn Bell Burnell was a 24-year-old graduate student at Cambridge when she noticed the signal that would become the first confirmed pulsar detection. She had been working with her supervisor, Anthony Hewish, on a newly built radio telescope, analyzing long strips of chart paper by hand, an enormous painstaking task, when she spotted something she described as a bit of scruff, a small, regular repeating signal that didn't match any known source of radio interference. After ruling out terrestrial sources after the LGM designation and the genuine uncertainty about what they were seeing after further investigation, revealed a second similar signal from a different part of the sky, which effectively ruled out an artificial origin, since two separate civilizations broadcasting on the same frequency in different directions was implausible. The nature of the signal began to clarify. Theoretical predictions made by Franco Pacini and Thomas Gold about rotating magnetized neutron stars fit the observations. A new class of astronomical object had been found. The Nobel Prize in Physics in 1974 was awarded partly for this discovery. Jocelyn Bell Burnell, who made the initial observation, was not among the recipients. The decision was and remains a subject of discussion in the scientific community. She herself has spoken about it with considerable grace over the years, more interested in the science than in the credit, and has gone on to a distinguished career in astrophysics that has earned her recognition of many other kinds. Her story sits in the background of every pulsar observation that has followed. Something found in scruff, in chart paper, in the patient attention of someone willing to look carefully at what others might have overlooked. Some neutron stars have magnetic fields so extreme that they occupy an entirely separate category objects called magnetars. Their surface magnetic fields are estimated to be 1,000 times stronger even than ordinary neutron stars, reaching intensities that are by any measure the strongest known magnetic fields in the universe. At these field strengths, strange effects arise. The magnetic field is strong enough to distort the electron clouds around atoms, to actually change the shape of atoms, stretching them along the field lines into elongated forms that bear little resemblance to the spherical electron distributions that exist in ordinary matter. The vacuum of space itself, near a magnetar, behaves in quantum mechanically unusual ways, becoming birefringent, meaning that different polarizations of light travel through it at slightly different speeds. Magnetars occasionally release bursts of energy starquakes caused by the sudden adjustment of stress in their rigid crystalline crusts that can be detected across the galaxy and sometimes beyond. In December of 2004, a burst from a magnetar located approximately 50,000 light-years away in the Large Magellanic Cloud released more energy in a fraction of a second than the Sun emits in 250,000 years. Despite the enormous distance, the burst was energetic enough to measurably ionize the upper atmosphere of Earth, affecting the ionosphere briefly but detectably, 50,000 light-years. And it still touched us. The universe is full of distances that feel like insulation. And then occasionally, something reminds you that distance is not the same as separation. Neutron stars can exist alone, or they can exist in binary systems paired with another star, or with another neutron star, or with a white dwarf, or in some cases with a black hole. When two neutron stars orbit each other in a tight binary, they lose energy gradually through the emission of gravitational waves, ripples in space-time produced by their mutual acceleration. As they lose energy, their orbit shrinks. They spiral inward slowly, at first, then faster still, over millions of years of gradual inspiral. When they finally merge, when two neutron stars collide, the event releases an enormous burst of gravitational waves and a flash of light across multiple wavelengths, including a distinctive type of gamma-ray burst and a slower optical and infrared glow called a kilonova. In 2017, the LIGO and Virgo gravitational wave detectors registered the signal of two neutron stars merging roughly 130 million light-years away. In the same moment, telescopes across the world and in space detected the accompanying light. For the first time, astronomers observed a single cosmic event simultaneously in both gravitational waves and electromagnetic radiation, a milestone that opened what researchers called the era of multi-messenger astronomy. And in the spectrum of the kilonova, scientists found evidence of heavy elements being produced in real-time gold, platinum, strontium, and other elements that can only form in conditions of extreme neutron density. The long-standing question of where the heaviest elements come from had in one observation shifted from theory toward confirmation. The gold in the world, in jewelry, in electronics, in the thin film on certain spacecraft components that protect against radiation is thought to have been forged largely in events like this one. in the merging of neutron stars hundreds of millions of light-years away and billions of years ago, creating a brief, brilliant explosion of nucleosynthesis before the material dispersed into the space that would eventually become the cloud from which our solar system formed, held now perhaps in something close to you, something small and ordinary, carrying in its atoms a memory of extraordinary violence from an unimaginable distance of time and space. There is a quality to the neutron star's existence, to the pulse's regular sweep, the magnetar's intense and periodic outbursts, the binary pairs slow in spiral, that is worth sitting with gently as this part of the night deepens. These are not chaotic things. They are precisely ordered. They spin on schedules. They pulse with a regularity that humans have used as scientific instruments. They follow their physics with a consistency that is almost formal, almost ceremonial. Extreme objects operating according to rules that do not bend. Psychologists who study rhythm and regularity have noted that the human nervous system tends to find regular patterns calming, that a consistent beat, whether in music or in breath or simply in the environment, has measurable effects on heart rate and on the quality of attention. The brain, it seems, relaxes slightly into predictability. It releases some of the monitoring effort it maintains against the unexpected, and that release has a felt quality, a settling. The pulsars out there in the galaxy spin on sending their regular signals into space, not for anyone in particular, not aimed, just sweeping, steady, reliable, the way certain things are reliable, not because they choose to be, but because the physics that underlies them admits no variation. And from here lying still, there is something almost companionable about that. The universe keeping its own kind of time in the dark, while you keep yours. The strangest endpoints of stellar life are still ahead in this quiet journey, the places where matter crosses a threshold beyond which not even light can return. Objects that are less a thing than a condition of space itself. Places where the known and the unknown meet at a boundary that for now cannot be crossed in either direction. There is a threshold in physics beyond which the usual descriptions begin to soften and dissolve. Not because the science becomes vague or because the measurements lose their precision, but because the thing being described genuinely resists the kinds of language that work well for other things. A black hole is not a hole exactly. It is not empty. It is not dark in the way a room without lights is dark. It is something for which the ordinary words were never designed, and which arrived in scientific understanding before anyone was entirely sure such a thing could exist at all. What it is at its most essential is a region of space where gravity has become strong enough to prevent anything, including light, from escaping. Not from slowing light down, not from bending it, from stopping it entirely, from ever crossing back to the outside. And at the center of that region, where the mathematics of general relativity produces a result that the equations themselves cannot comfortably handle, something sits that physicists call a singularity, a place where density becomes theoretically infinite, and where the current framework of physics quietly admits that it does not fully know what it is describing. That admission is not a failure of science. It is, in a way, one of the more honest things science does, standing at the edge of what it knows and saying clearly that the edge is there. A stellar black hole forms when a massive star, one generally thought to require more than roughly 20 to 25 times the mass of the Sun. Though the exact threshold depends on factors still being refined, undergoes core collapse and produces a remnant whose mass exceeds the limit that neutron degeneracy pressure can support. Where a slightly less massive collapse halts at the neutron star stage, a more massive one does not halt. The collapse continues past neutron density, past any known pressure capable of resisting it, and the remnant compresses without limit, or rather toward a singularity that general relativity predicts but cannot fully describe. The boundary around this region, the surface from within which nothing can escape, is called the event horizon. It is not a physical surface. There is no membrane there, no edge you could touch or see. It is a boundary defined purely by the mathematics of escape velocity. At any given distance from a sufficiently massive compact object, there is a minimum speed required to escape its gravity. At the event horizon, that required speed equals the speed of light. And since nothing with mass can reach or exceed the speed of light, and since even light itself cannot quite make it out from within that boundary, the interior is effectively sealed off from the outside universe. From the outside, you cannot see in. Information in the physical sense cannot reach you from beyond that boundary. Whatever happens inside a black hole stays inside a black hole, not as a rule of secrecy, but as a consequence of the geometry of space-time in that region. The size of the event horizon, its radius called the Schwarzschild radius, after the physicist Karl Schwarzschild, who derived it from Einstein's equations of general relativity in 1916, while serving on the Russian front during the First World War, depends only on mass. The Schwarzschild radius of an object is proportional to its mass and nothing else. For the Sun, the Schwarzschild radius is about 3 kilometers. If you could compress the entire mass of the Sun into a sphere 3 kilometers across, it would become a black hole. For Earth, the equivalent radius is about 9 millimeters smaller than a marble. Neither the Sun nor the Earth will actually become black holes. Their masses are insufficient to compress them to those densities through gravitational collapse alone. This is a common misunderstanding. Black holes do not form from just any object, and they do not wander through the galaxy consuming everything they encounter. They form from the depths of sufficiently massive stars. They occupy specific regions of space, and their gravitational influence at a distance is no stronger than the original stars would have been. A black hole, where the Sun currently sits, would not pull the planets inward. The planets would continue in their orbits exactly as they do now. The gravity at a given distance does not change when a star collapses. It is the same mass concentrated differently, but felt the same from outside. The danger of a black hole, if that is even the right word, is proximity. And the universe is mostly very large. Astronomers have found black holes across a remarkable range of masses. Stellar black holes, the kind that form from individual massive stars, typically range from a few times the mass of the Sun up to roughly 100 solar masses, though some recent detections have suggested objects potentially larger even than that. These are scattered throughout the galaxy, the dark remnants of stars that burned bright and briefly and ended in collapse. At the other end of the scale sit the supermassive black holes, objects containing millions to billions of solar masses found at the centers of most large galaxies, including the Milky Way. At the center of our galaxy, roughly 26,000 light-years from Earth, sits a supermassive black hole, designated Sagittarius A star, containing roughly 4 million times the mass of the Sun. It is not actively consuming material in any dramatic way at present, and so it is, by the standards of active galactic nuclei in other galaxies, remarkably quiet. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow. The silhouette cast by the event horizon of the supermassive black hole at the center of the galaxy, Messier 87, located about 55 million light-years from Earth. That black hole contains approximately 6.5 billion solar masses. The image, assembled from radio telescope observations coordinated across 8 observatories on different continents, showed a bright ring of emission surrounding a central dark region, the photon ring and the shadow. It was the first direct visual evidence of a feature that general relativity had predicted for over a century. 2 years later, a similar image was released of Sagittarius A star, closer but also smaller and faster changing, which made it technically more challenging to image. Both images arrived in the world quietly, without the fanfare that their significance perhaps warranted, or perhaps exactly with the kind of attention they deserved, thoughtful, steady, received by people who understood what they were looking at. The region around an actively feeding black hole, when material from a companion star or a surrounding gas cloud is spiraling inward, is called an accretion disk. As material falls inward toward the event horizon, it doesn't fall straight in. It orbits, forming a flattened disk of gas and dust that spirals inward, gradually heating as it does through friction and compression. The inner edge of the accretion disk, just outside the event horizon, reaches temperatures of millions of degrees, radiating intensely across X-ray and even gamma-ray wavelengths. This is why some black holes are among the brightest X-ray sources in the sky, despite the black hole itself emitting nothing. The brightness comes from the material outside the event horizon, from the violent process of infall and compression in the accretion disk, from the energy released before anything crosses the boundary. The black hole itself, at the center, remains as dark as its name suggests, but everything falling toward it blazes. Some black holes also produce jets, narrow beams of plasma, and magnetic field lines that emerge perpendicular to the accretion disk and extend for thousands of light years into the surrounding space. The mechanism that produces these jets is not yet fully understood. The energy and direction of the jet appear to be connected to the spin of the black hole and the configuration of its magnetic field, but the precise physical process that accelerates material to nearly the speed of light and collimates it into such narrow beams remains an active area of research. It is one of the open questions sitting in the middle of an otherwise well-developed field. The jets from distant, extremely luminous black holes, objects called quasars, the active galactic nuclei of early galaxies, powered by supermassive black holes consuming enormous quantities of material, can be seen across billions of light years. They are among the brightest persistent sources of energy in the observable universe. Objects that, if placed at the distance of the nearest stars, would cast shadows on the ground at night. There is a theoretical prediction associated with black holes that remains unconfirmed by observation, but has become one of the most discussed ideas in theoretical physics. In the 1970s, Stephen Hawking demonstrated using a combination of quantum mechanics and general relativity that black holes should very slowly emit thermal radiation energy arising from quantum effects at the event horizon. This radiation, now called Hawking radiation, would carry energy away from the black hole over extraordinarily long timescales, causing it to very gradually lose mass and eventually evaporate entirely. The timescale for this process for any black hole of stellar mass or larger is so vast as to be practically inconceivable, many orders of magnitude longer than the current age of the universe. Hawking radiation from an existing stellar black hole is so faint that detecting it is, with any foreseeable technology, essentially impossible. The prediction has never been confirmed observationally, and yet physicists take it seriously because the mathematics that produces it is grounded in well-established principles, and because the questions it raises are genuinely profound. If black holes eventually evaporate completely, what happens to the information about all the matter that fell into them? Does it escape in some encoded form in the Hawking radiation? Is it lost entirely in violation of a fundamental principle of quantum mechanics? Or does something else happen? something that the current framework doesn't fully anticipate. This is called the black hole information paradox, and it sits at the intersection of the two great theoretical frameworks of modern physics, quantum mechanics, and general relativity, which agree with each other extraordinarily well in the regimes where they have both been tested, but which produce irreconcilable results when pushed to the extremes that black holes represent. The resolution of this paradox, when it comes, will likely require new physics, a deeper framework not yet found. Some of the most careful thinkers in theoretical physics have spent decades on this question. It remains genuinely open. The human mind neuroscientists have observed responds to the concept of the unknowable in interesting ways. When presented with a limit, a genuine principled boundary beyond which information simply cannot reach the brain, does not necessarily experience this as frustration. For many people, the sense of a boundary that cannot be crossed produces something closer to a kind of release, the permission to stop trying to imagine what lies beyond it, the recognition that not knowing something is not the same as something being wrong. There is a particular quality to limits that are not failures but features. The edge of a map that says simply, "Here is as far as we can go. Not yet, perhaps not ever." The horizon that recedes as you approach it. Black holes are the universe's most formal statement of that kind of boundary. Here is a place where the physics you know no longer applies. Here is a region from which no information escapes. Here is an edge built into the fabric of reality that is simply part of how things are. And beyond that boundary, the equations whisper something about singularities, about infinite density, about conditions they cannot quite describe. And the science at that whisper falls respectfully quiet. Not all of the universe's stranger stars announce themselves through the drama of black holes and neutron stars. Some of the most quietly remarkable stellar objects are the ones that don't fit cleanly anywhere in the main sequence, the ones that change, the ones that are paired, the ones that exist in between categories or straddle the boundaries between what we expect and what we find. The night still holds time for them. Stars that pulse with a rhythm, almost like breathing. Stars that share their light with a companion in orbits so long and slow that a single revolution takes longer than human civilization has existed. Stars that vary in brightness, not through explosions, but through something more subtle, the geometry of their surroundings, the wobble of something orbiting them, the shape of their own atmosphere in motion. They are the exceptions that, gathered together, begin to suggest that the categories were always approximations, that the universe is more continuous, more gradual, more willing to produce things that sit between labels than any classification system quite captures. Not every star holds still. This seems like a simple observation, but it carries more inside it than it first appears. All stars move in the broad sense, orbiting the galactic center, drifting relative to their neighbors, spinning on their axes. But some stars change in ways that go deeper than motion. They breathe, they fluctuate, they grow brighter, then dimmer, then brighter again, in patterns that repeat with a regularity that astronomers have learned to read the way you might read a pulse. These are the variable stars, and they have turned out to be among the most scientifically useful objects in the sky, as well as some of the most quietly fascinating. The variation in a star's brightness can arise from several entirely different causes, and distinguishing between them, understanding what kind of variability a particular star is displaying, tells you something specific about what is happening inside it or around it. Some stars vary because they physically pulsate. Their outer layers expand and contract in a rhythmic cycle, driven by processes deep in the stellar interior. As the star expands, its surface cools and dims slightly. As it contracts, it heats and brightens, the whole star breathing in and out across days or weeks or months, its light level rising and falling with each cycle. The Cepheid variable stars are the most scientifically important members of this pulsating category. They are large, luminous, yellow-white supergiant stars that pulsate with periods ranging from a few days to a few months. And what makes them extraordinary is a relationship discovered in the early 20th century by an astronomer named Henrietta Swan Leavitt, who was working at the Harvard College Observatory, the same institution where Annie Jump Cannon was cataloging stellar spectra in the same era through similarly painstaking observational work. Leavitt was studying variable stars in the Small Magellanic Cloud, a small satellite galaxy visible from the southern hemisphere. Because all of the stars in the Small Magellanic Cloud are approximately the same distance from Earth, differences in their apparent brightness reflect real differences in their intrinsic luminosity. Leavitt noticed something in her data that no one had seen before: a clear, consistent relationship between the period of a Cepheid's pulsation and its intrinsic luminosity. The longer the period, the more luminous the star. This period luminosity relationship, Leavitt's law, as it is sometimes called, though it took decades for her contribution to receive its proper recognition, became one of the most powerful tools in the history of astronomy. By measuring a Cepheid's pulsation period, you can calculate its true luminosity. By comparing that to how bright it appears from Earth, you can calculate its distance. Cepheids became and remain standard candles, objects of known intrinsic brightness used to measure distances across the universe. It was observations of Cepheid variables in the Andromeda Galaxy that allowed Edwin Hubble in 1923 to establish that the Andromeda Nebula was not a cloud of gas within the Milky Way, but a separate galaxy at a distance of roughly 2 million light-years. A measurement that fundamentally changed humanity's understanding of the scale of the universe, and it rested entirely on a relationship noticed by a woman examining photographic plates, tracing patterns in numbers, in a room at Harvard where women were paid 25 cents an hour. Not all variable stars pulsate from within. Some vary because of what surrounds them or what passes in front of them. Eclipsing binary stars are systems where two stars orbit each other in a plane oriented such that from Earth's perspective, one star periodically passes in front of the other. When the brighter star is partially or fully blocked, the combined brightness of the system drops. When it reappears, the brightness returns. The result is a light curve, a graph of brightness over time that dips and recovers in a pattern directly reflecting the geometry of the orbit. The first eclipsing binary to be recognized as such was Algol in the constellation Perseus, a star that had been noticed for centuries to change brightness regularly and which was sometimes called the Demon Star, possibly because its behavior seemed inexplicable by the standards of the time. The Arabic name Al-Ghul, from which Algol derives, may have carried some awareness of its strange flickering, though the interpretation is uncertain. The eclipsing nature of the system wasn't understood until the late 18th century. Algol is actually a triple system, 3 stars in a gravitationally bound arrangement, 2 of which produce the visible eclipse every 2 days and 20 hours or so, with the dimming lasting roughly 10 hours, as the cooler, larger star partially occults its brighter, hotter companion. The study of eclipsing binaries has allowed astronomers to determine stellar masses and radii with a precision that is difficult to achieve any other way. When 2 stars orbit each other in a well-characterized system, the orbital period and the shapes of the light curves can be used to calculate the masses of both stars, their relative sizes, the distance between them, and the inclination of their orbit. These systems are in a sense the universe's own scales, built into the sky, available to anyone patient enough to watch and measure. Binary stars in general represent one of the more unexpectedly common features of the stellar landscape. Estimates vary considerably depending on the mass range being considered, but for stars similar to or more massive than the Sun, it appears that the majority exist in multi-star systems rather than as solitary objects like our own Sun. Some estimates suggest that more than half of all Sun-like stars have at least one companion. Why does this matter beyond the immediate scientific interest in measuring stellar properties? Because the presence of a companion star changes sometimes fundamentally the way a star lives and dies. A star in a binary system can transfer mass to its companion, altering both of their evolutionary trajectories. It can be spun up or slowed down by tidal interactions. In close binaries, tidal forces can circularize orbits over time and lock the rotational periods of both stars to their orbital period, a stellar version of the same process by which the Moon always shows the same face to Earth. And as discussed in the context of white dwarfs and neutron stars, the endpoint of a binary system's evolution, when one or both stars have died, can produce phenomena that solitary stars simply cannot. The Type 1, a supernova. The kilonova mergers. The millisecond pulsars spun up by accreted material. The hypervelocity stars flung outward by the asymmetric deaths of their companions. Stellar companionship, it turns out, is not merely circumstantial. It shapes destinies. There is a category of variable star whose variation arises not from pulsation or eclipse, but from the star's own rotation, from the fact that its surface is not uniform. Spotted stars, stars with chemical patches, stars with regions of different temperature distributed unevenly across their surfaces, all show a periodic brightness variation as they rotate and present different faces toward Earth. Star spots, analogous to the sunspots on our own Sun, but sometimes covering much larger fractions of the stellar surface, are regions where intense magnetic fields suppress convection and create cooler, darker patches. On some active stars, particularly young, rapidly rotating stars, the star spot coverage can be dramatic. Researchers have inferred spot coverage fractions of 20 or 30% on some highly active stars compared to the Sun, where spots rarely cover more than a fraction of a percent of the surface at any time. The variation produced by star spot rotation is typically subtle and smooth, a gentle rise and fall in brightness over the stellar rotation period, sometimes with complex structure reflecting multiple spot groups at different longitudes. It is a quiet kind of variability, unspectacular, something you would notice only by watching carefully over time, with instruments sensitive enough to detect small changes. And yet this subtle brightness variation, extracted from the light curves of distant stars, has allowed astronomers to measure the rotation periods of thousands of stars, an otherwise nearly impossible measurement to make. The Kepler Space Telescope, launched by the National Aeronautics and Space Administration in 2009 to search for planets transiting their host stars, produced light curves of extraordinary precision for over 150,000 stars over 4 years. From those light curves, rotation periods were extracted for tens of thousands of stars, producing the largest catalogue of stellar rotation rates ever assembled. Rotation rate turns out to be connected to a star's age. Young stars rotate quickly. As they age, their stellar winds carry away angular momentum, the same process that the Sun's solar wind is enacting very slowly on the Sun, and they spin down. By calibrating the relationship between rotation rate and age across stars of known age, astronomers can estimate the age of a star from its rotation period. This technique, called gyrochronology, provides one of the most useful stellar age clocks currently available. The Sun, by this measure, is rotating at a rate consistent with its known age of about 4.5 billion years. A quieter, slower rotation than it had in its youth. Still turning, still maintaining a magnetic cycle, still producing sunspots and solar flares, but with a mature steadiness quite different from the turbulent activity of very young stars. Among the most visually striking variable stars are a subgroup called long-period variables, cool giant and supergiant stars that pulsate with periods ranging from roughly 100 days to over 1,000 days, and whose brightness can vary by enormous factors across a single cycle. Some of these stars, called Mira variables, after their prototype, Mira, in the constellation Cetus, can change in brightness by a factor of several hundred between their brightest and faintest phases. Mira itself, a red giant in the late stages of stellar evolution, roughly 200 to 400 light-years away, varies between roughly magnitude 2, easily visible to the naked eye, and magnitude 10, requiring a telescope over a period of approximately 332 days. At its brightest, it is one of the more notable stars in the sky. At its faintest, it is completely invisible without optical aid. The same star in the same region of sky, present and absent on a timescale of months. It was discovered to be variable in the 16th century, and the name Mira, wonderful in Latin, reflects the astonishment its behavior produced in the astronomers who first systematically documented it. Something they expected to be fixed was changing. Something they thought they understood was doing something new. That quality of surprise, the sky not quite holding still under careful observation, has driven astronomical discovery throughout the history of the science. The stars that didn't behave as expected, the signals that didn't fit any known source, the brightness dip that shouldn't be there. Time and again, the anomalies in what was assumed to be a stable background have turned out to be the most interesting things in the data. There is something gently relevant in the idea of variability at this hour of the night. Neuroscientists who study the sleeping brain have found that sleep itself is not a uniform state. It cycles through distinct phases: lighter sleep, deeper sleep, the rapid eye movement phase, where dreaming is most active, and then back again, in a pattern that repeats roughly every 90 minutes through the night. The brain's electrical activity changes substantially between these phases, shifting from the high-frequency complex patterns of wakefulness into the slower, more synchronized rhythms of deep sleep, and then into the distinctive rapid, low-amplitude waves of dream sleep. This cycling is not a flaw in the sleep architecture. It appears to be essential. Different stages of sleep seem to serve different functions: memory consolidation, physical restoration, emotional processing, the clearing of metabolic waste products from the brain's tissues through a system that operates primarily during sleep. The variation is the point. The movement between states is what makes the whole system work. A star that holds perfectly still at constant brightness reveals less about itself than one that varies. It is in the variation, in the pulsation, the dimming, the brightening, that the internal structure becomes legible. The star, by changing, allows itself to be known. Perhaps rest works the same way. Not in the holding still, but in the cycling. Not in the silence, but in the movement through different depths of quiet. The sky above, full of stars that are changing in ways too subtle or too slow for unaided eyes to detect, offers something that daylight rarely allows: the sensation of being inside something very large and very old, something that has been doing what it does for far longer than anything human, something that will continue long after. And within that enormous continuity, all of this variation, all of this quiet, persistent complexity, stars that breathe, stars that share their light with a companion, stars that rotate a slightly cooler face toward you every few days, faithful and unannounced. The universe does not simplify neatly. It offers categories, and then it offers exceptions, and the exceptions gathered patiently reveal that the categories were always descriptions of a tendency rather than walls around a fixed thing. And the night, which seemed at the start of this long drift to be simply dark, turns out to be full of exactly this kind of complexity. Quiet on the surface, rich underneath. There is one more place this journey will go before it lets you rest entirely. Back in a gentle way to where everything began, not with a beginning in the dramatic sense, but with the simplest thing. The sky as it is, the stars as they are. All of them, every kind, present at once above you in the dark that has been holding them all along. The Milky Way contains somewhere between 100 billion and 400 billion stars. That range, that uncertainty spanning hundreds of billions, is itself a kind of testament to how genuinely difficult it is to count what is out there. Not because the tools are inadequate, but because the galaxy is so large and so much of it is obscured by dust, and because what counts as a star at the faint, dim end of the mass distribution is itself a question with soft edges. The number is real. It is just too large for precision to feel like the right relationship to have with it. And the Milky Way is one galaxy among an estimated 2 trillion in the observable universe. 2 trillion galaxies, each containing billions of stars. Each of those stars with its own temperature, its own mass, its own age, its own particular history of nuclear burning and magnetic activity and orbital dynamics. The number of individual stellar objects in the observable universe is estimated very roughly at somewhere around 10, followed by 24 zeros. A 1 with 24 zeros behind it. There is no useful way to hold that number in the mind, but there is a way to let it arrive without trying to hold it, to let it pass through, the way a large wave passes through water without the water going anywhere. The number is there. You don't need to contain it. It simply is. What the long journey through stellar types tonight has perhaps quietly assembled, not as a lesson, but as an accumulated texture of understanding, is a sense of the range. The genuine extraordinary range of what a star can be. From the smallest red dwarfs burning for trillions of years at temperatures low enough that molecules form in their outer atmospheres to the most massive blue supergiants consuming themselves in millions of years and pouring energy into space at rates that dwarf everything around them. From the patient white dwarfs cooling through epochs too long to name to the neutron stars spinning hundreds of times per second in the dark. From the variable stars breathing in and out over days and months to the binary pairs locked in gravitational partnership across orbits that take centuries to complete. From the sun, ordinary middle-aged stable, keeping everything here alive, to the black holes that mark the places where the physics of the familiar world quietly excuses itself. All of this fits within a single category of object, a star, a gravitationally bound sphere of plasma undergoing nuclear fusion. That one description, simple enough to state in a single sentence, contains multitudes. Researchers who study the distribution of stellar types across the galaxy have found that this variety is not random. It reflects the history of the galaxy itself, the way conditions for star formation have changed over time, the way successive generations of stars have enriched the available material with heavier elements, the way different regions of the galaxy favor different kinds of star birth. The inner regions of the galaxy, denser and more chemically evolved, tend to host different stellar populations than the outer regions where conditions are more similar to what the early galaxy looked like billions of years ago. Stars, in this sense, carry their origin in them. The chemical composition of a star's atmosphere reflects the composition of the cloud it formed, from which reflects the history of nucleosynthesis that had occurred in that region of the galaxy before it was born. An older star formed when the galaxy was young has fewer heavy elements in its atmosphere, a lower metallicity in astronomical terminology than a younger star formed from material that has been through multiple rounds of stellar processing. The Sun's metallicity places it at a middle point, not among the most ancient stars in the galaxy, not among the most recently formed. A second or third generation star formed from material that had already been through at least one round of stellar birth and death before the Sun condensed from its natal cloud. This is not a small detail. The heavy elements in the Sun and in the planet that formed around it and in the living things on that planet are there because an earlier generation of stars lived and died before the solar system existed. The carbon and oxygen and iron and calcium that the Sun and Earth and every organism on Earth contain are there because other stars forged them and released them. The solar system is chemically a product of stellar history, not the history of one star, but of many. Neuroscientists who study how the brain processes deeply connected information ideas that link the self to something larger have noted a particular kind of cognitive softening that occurs in these moments. When the mind encounters a fact that genuinely connects personal existence to something enormous and ancient, there is often not an expansion of alertness, but a reduction of it, a settling. The boundaries of the self, becoming slightly less defined, slightly less defended. Something that resembles in its physiological signature the early stages of sleep. It is as though the brain, recognizing that it is part of something, it cannot fully separate itself from releases the effort of maintaining the separation. The connection between stellar nucleosynthesis and biological life is not metaphorical. It is a physical, traceable chemical connection. The carbon in every living cell on Earth was produced in the helium-fusing cores of aging stars. The oxygen was produced in those same cores and in the supernovae that followed. The iron that carries oxygen through human blood was forged in the final stages of massive stars before their cores collapsed. These elements traveled through space as part of the interstellar medium, were gathered into the cloud that became the solar system, were incorporated into the young Earth, were cycled through geological and biological processes across billions of years, and are now, in their present form, the physical substrate of thought and breath and warmth. When scientists say that humans are made of stardust, they are not speaking loosely. They are describing a literal chain of physical causation that connects the atoms in your body to specific processes in specific stellar objects that existed before the solar system. The connection is measurable. It is written in isotope ratios and elemental abundances that can be traced backward through time, through geological and astronomical records, towards the stellar environments where those atoms were built. You are in the most literal available sense part of the ongoing story of what stars do. Not a spectator to it, not merely adjacent to it. Part of it, assembled from its outputs, sustained by one of its current members, made of material that has already passed through fire more than once. There is something that happens to attention at this depth of the night that is worth acknowledging gently. The psychologist Mihaly Csikszentmihalyi described a state he called flow, a condition of deep, effortless engagement where attention is fully absorbed and the usual monitoring of self and situation falls away. But there is a different state, less discussed, that some researchers have begun to explore, a condition of open, diffuse attention where the mind is awake but not focused, present but not directed, alert but not searching. This state has various names in different research traditions. Some neuroscientists call it the default mode network state, the mode the brain enters when it is not engaged with a specific external task, when it is allowed to wander, to associate freely, to process without agenda. This network, which involves regions of the medial prefrontal cortex and the posterior cingulate cortex and several other areas, becomes more active, not less, when focused, external attention relaxes. The default mode network is associated with autobiographical memory, with mental simulation, with the processing of social and emotional information, and with the kind of loose drifting thought that can occur in the period between wakefulness and sleep. It is not an idle network. It is, researchers suggest, doing something, consolidating, integrating, making connections that focused attention tends to interrupt. Lying still in the dark, listening to something that doesn't demand anything, this may be one of the conditions that allows the default mode network to do its quiet work. The thoughts that drift through this state, the images and memories and half-formed associations, are not distractions from something. They are the process itself. The mind left to its own devices, doing what it does when no one is asking it for anything specific. The stars have been providing this kind of backdrop for as long as humans have been conscious enough to notice them. A presence in the dark that is real and enormous and somehow unconcerning. Something to look toward without needing to do anything about it. The concept of a stellar population, a group of stars that form together from the same cloud at roughly the same time, gives astronomers a way to study stellar evolution across many stars simultaneously. Star clusters are the most accessible examples, gravitationally bound groups of stars all the same age and initial composition, spread out in space, but still moving together through the galaxy. Open clusters like the Pleiades, visible in the northern sky, contain hundreds to thousands of stars and are relatively young. The Pleiades are estimated at around 100 million years old, making them very young in stellar terms, still containing hot blue stars that have not yet had time to exhaust their fuel. Globular clusters, by contrast, are ancient spherical collections of tens of thousands to millions of stars, often more than 10 billion years old, orbiting the galaxy in halo regions above and below the disk. The stars in globular clusters are on average among the oldest in the galaxy, and their light has been traveling outward since an era when the universe itself was much younger. Looking at a globular cluster with even a modest telescope, seeing that compressed luminous sphere of ancient stars produces a particular kind of impression. Something about the density, the age, the collective light of millions of stars that have been burning together for longer than Earth has existed, arriving at your eye simultaneously. An impression that is difficult to name precisely, but that several people who have written about it have described as a sense of weight. Not heaviness, more like significance arriving physically through the light. Some experiences are processed not through analysis, but through something more immediate. The way a landscape can arrive in the body before the mind has named it. The galaxy in the long view is a self-renewing system, though that renewal takes place on timescales that make the word slow seem inadequate. Material from dying stars enriches the interstellar medium. That enriched material eventually collapses into new stars, often bringing along enough heavy elements to form rocky planets around them. Those planets, in at least one documented case, develop conditions where chemistry becomes biology and biology becomes the kind of complex, organized matter that can look back at the stars and wonder about them. Whether that last step has happened elsewhere is still genuinely unknown. Researchers studying the conditions for life, the distribution of potentially habitable planets, the prevalence of the necessary chemical building blocks, the stability requirements for the long time scales that complex life seems to need have not yet found definitive evidence of life beyond Earth. The search continues carefully across multiple approaches, but the question remains open in the most honest sense, not answered, not ruled out, simply not yet resolved. What is known is that the material requirements for life as we know it, which is the only version we can currently study in detail, are not rare. Carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. The elements that make up the vast majority of biological molecules are among the most abundant elements in the universe. They are produced by the most common categories of stellar processes. They are distributed widely through the interstellar medium and incorporated into planetary systems wherever the right conditions align. Life, if it is anywhere else, is made of the same things, assembled by the same physics, lit by some version of the same stellar fire. The oldest light in the observable universe is not starlight. It is the cosmic microwave background, the afterglow of the era, roughly 380,000 years after the universe began, when the cosmos cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time, allowing light to travel freely for the first time. That light has been traveling for nearly 13.5 billion years. It arrives from every direction, uniformly carrying within its tiny temperature variations, the seeds of all the structure that later developed the galaxies, the clusters, the filaments and voids of the cosmic web. Stars came later. The first stars are thought to have formed somewhere between 100 and 200 million years after the beginning, massive metal-free burning brilliantly in a universe that had not yet developed any of the complexity that followed. Those stars have been gone for billions of years. Their light is too old and too redshifted for current telescopes to detect directly. They exist now only in theory, and in the faint chemical signatures they left behind traces of their deaths in the composition of the oldest surviving stars. We sit downstream of all of it, downstream of the first stars, downstream of generations of stellar birth and death, downstream of the slow chemical enrichment of a galaxy, downstream of a particular cloud's collapse 4.5 billion years ago into a star and a system of planets, downstream of the geological and biological processes that shaped this specific planet into something hospitable to the particular kind of awareness that is right now in this room, holding all of this very lightly, beginning to let it go. The night has been long, the drift has been far, and everything that was moved through every type of star, every kind of ending, every fact about light and temperature and mass and time has been in its way a description of the same continuous thing. Matter organized by gravity and physics and time into objects that burn and cool and end and leave behind what the next generation needs. The sky above holds all of it at once. Every type, every age, every stage, present together in the dark. And the last place this journey will settle gently without arrival is simply there, in that sky, in the stillness of looking up one more time before the night does what nights do. The sky doesn't know you're watching. That's one of the quieter things about it. All of this, the red dwarfs burning patiently below the threshold of visibility, the white dwarfs cooling through their long afterward, the pulsars sweeping their beams through the dark with perfect regularity. None of it is arranged for an audience. None of it is performing. It is simply continuing the way it has continued for billions of years, with a consistency that doesn't require acknowledgement to persist. And yet, here you are, having moved through all of it tonight, having let it pass through, or having drifted somewhere alongside it, or having simply been present while it arrived and kept going. That is enough. That has always been enough. There is a phenomenon that astronomers observe called astronomical seeing, the measure of how steady the atmosphere is on a given night, how much the air above a telescope is turbulent or still. On nights of good seeing, star images in a telescope are sharp and steady, holding their shape without flickering. On nights of poor seeing, the images dance and blur, the atmosphere too restless to let the light through cleanly. The atmosphere is always moving. Even on the calmest night, the air above you is layered with different temperatures, different densities, different wind currents, at different altitudes, all of them bending the starlight slightly as it passes through, all of them contributing to that characteristic twinkling that makes stars seem alive in a way that planets seen with the naked eye do not. Planets appear too large in angular size for the twinkling to be visible. The variations average out across their disk. But stars, point sources of light, even in the largest telescopes, show every flicker that the atmosphere introduces. Researchers who study atmospheric optics have found that the twinkling of stars is actually a remarkably complex process, not simply a random flickering, but a structured interference pattern produced by pockets of air of different refractive indices moving through the line of sight. The pattern is called a scintillation pattern, and it moves across the ground at speeds that can range from a few meters per second to much faster, depending on the wind at the relevant altitude. If you could see the pattern on the ground, it would look like a rapidly shifting interference pattern of light and shadow, something like sunlight on the bottom of a shallow pool, but moving. Your eye, sampling the pattern from a single fixed point, sees only the rapid variation, the twinkling. The underlying pattern with its structure and motion is invisible from any single vantage point. You see the effect, not the cause. This is in various ways how a great deal of perception works. The brain receives an effect and constructs a cause from it. The twinkling star is not twinkling exactly, the star is steady. It is the air between you and it that moves, and the eye that registers the result. The star at its distance knows nothing of any of this. The light arriving at your eye right now from the night sky, if you were outside, if the sky were clear and dark, has been traveling for different lengths of time from different sources. The nearest stars are a few light years away, their light a few years old. The stars of the familiar constellations are typically tens to hundreds of light years distant, their light arriving from decades or centuries ago. The Andromeda Galaxy, visible as a faint smudge to the naked eye, is approximately 2.5 million light-years away. That light began its journey before the genus Homo existed on this planet. All of this arriving simultaneously, all of it mixing on the retina. The near and the ancient, indistinguishable without the instruments and the mathematics that separate them. The human visual system, neuroscientists have found, does not process all of what arrives at the eye. It samples, it selects, it builds a model of what is likely to be there based on what has been seen before, and uses the incoming light to confirm and adjust that model rather than to construct perception from scratch with each moment. Seeing is not passive reception. It is active prediction, continuously updated. What this means for the night sky, for the experience of standing under it, or lying under it, or simply knowing it is there, above the ceiling, is that what you perceive is partly the sky and partly you, partly the photons and partly the model your nervous system has built across a lifetime of looking. The experience of the night sky is a collaboration between the universe and the observer. And that observer brings everything memory, emotion, the particular way this night feels, the weight of the day that preceded it, to the act of looking up. The sky receives all of this without comment. it simply continues. Sleep, when it comes, arrives through a particular sequence of transitions that neuroscientists have mapped in considerable detail. The brain shifts from the relatively fast, irregular electrical activity of wakefulness into slower, more synchronized rhythms. Body temperature drops slightly by roughly 1 to 2 degrees Celsius, a cooling that the brain appears to actively regulate, redirecting blood flow toward the hands and feet to allow heat to dissipate from the body's core. Heart rate slows, breathing deepens and becomes more regular. The muscles that have been maintaining posture and readiness across the day gradually release their tone. This sequence does not happen all at once. It is a gradual process, taking many minutes, passing through transitional states where the mind is neither fully awake nor fully asleep. In this hypnagogic zone, the territory between wakefulness and sleep, unusual things can happen. Images arise without being summoned. Fragments of thought drift through without connecting to anything. The sense of the body becomes uncertain, its boundaries softening its weight, becoming strange. Researchers have found that this transitional state is associated with a characteristic brainwave pattern called the theta rhythm, slow, regular oscillations occurring several times per second, different from both the alert beta rhythm of wakefulness and the deep delta rhythm of slow-wave sleep. The theta state is also associated with certain kinds of creativity and with the retrieval of distant memories, as though the loosening of ordinary conscious control allows other quieter processes to surface. Some people report in this state a sensation of falling, a brief involuntary muscle jerk called a hypnic jerk that pulls them back toward wakefulness momentarily. Scientists are still exploring the precise mechanism, but one theory suggests it may be related to the brain, misinterpreting the relaxation of muscle tone as a loss of balance, a vestigial alarm response from an evolutionary context where losing muscle tone while upright would indeed mean falling. The body, in its own way, still carries old architectures, old responses built for different circumstances, still running quietly in the background, occasionally making themselves known. The stars above you tonight will still be there when the sun rises. They don't leave. They are simply outshone the sky, brightening around them, until they become invisible, present, but overwhelmed by the closer, nearer light of the sun moving back into view as Earth continues its rotation. The red dwarfs are still burning. The white dwarfs are still cooling imperceptibly through another night. Somewhere in the galaxy, a pulsar is completing thousands of rotations while you lie still. Somewhere, a binary pair has moved a small fraction of a degree further along its orbit. A Cepheid variable is somewhere in its pulsation cycle, expanding slightly, its surface temperature shifting by a few hundred degrees, its light changing in a way that no human eye is currently pointed at. The universe keeps its own pace. It does not slow for night, or for sleep, or for the quiet that settles over a room when the day has finally ended. It continues patient, indifferent, and in its indifference, somehow reliable. Something that will be there in its complexity and its scale, unchanged in any meaningful way, if you return to it in the morning, or in a year, or in a lifetime. There is a particular comfort in that which doesn't need to be examined too closely to be felt. The body knows things the mind takes longer to reach. It knows when to release. It knows when the effort of the day has been sufficient, when the holding can stop, when the long accumulation of sensory input and decision and response has reached its natural limit for this particular rotation of this particular planet. It knows this in the cooling of the skin and the slowing of the breath and the way the eyes, even when closed, stop searching. Physiologists who study the onset of sleep have noted that one of the most reliable indicators of the transition is not any single measurement, but a combination the convergence of slowing heart rate, dropping core temperature, and the first appearance of slow oscillations in the electroencephalogram. When these arrive together, sleep is close. The system is ready. Something in the body has decided, without consultation, that it is time. You do not have to do anything for that to happen. You only have to be here, in whatever position is comfortable, with whatever thoughts are moving through, not held, not followed, just passing. The stars above the ceiling are various and ancient and burning and cooling and spinning and drifting, and some of them have planets, and some of those planets may have something on them that is also lying still tonight under its own sky, made of atoms forged in the same kinds of fires, existing because the universe has this particular tendency to organize matter into things that for a while wonder about their surroundings. The wondering can rest now. It has gone far enough tonight, from the familiar warmth of a sun-like star to the dim patience of a red dwarf, from the cooling crystal of a white dwarf to the spinning precision of a pulsar, from the blue supergiant's brief brilliance to the quiet threshold of a black hole's edge. All the way out to the oldest light, the chemical origins, the connections written in isotope ratios between the atoms in living things and the stars that made them. All the way out, and now gently back to the room, to the weight of the body, to the breath which has been there the whole time, moving in and out without being asked, the same as it always does, the same way the sun does what it does without being asked, the same way the smallest stars burn without requiring attention. You are part of a universe that continues, that has been continuing for a very long time, that will continue for much longer still. And tonight, your part in it is simply to rest. The stars will hold the sky. You don't need to.